Well. Am I live, guys? Am I audible and visible? Can you all see me and hear me? Hello, everybody. Longest time, isn't it? How are you all? Very excited for today's class. What's up and how are you all doing? Niranjan Guru, start spamming the chat box, huh? Okay. All right, everybody. Like I always say, namaskara, everyone. Andariki namaskaram, ellargu swagatam, and a very warm vanakkam to your Vedanta J English channel. It's been a long time, but here we are, and today we are going to complete two chapters, that is coordination compound and DNF block. We are live, everybody, and I need you all to call up all your friends, everybody. Yes. So today we are going to complete two of the most high weighted chapters, which you know, and if we look at the last 10 years question paper, we will get to see that more than 153 questions have actually come from this chapter, everybody. So there is no way we can let this chapter go, and it is a very important chapters, basically two chapters. That is, and these two chapters are very quite very closely knit together. Like DNF block, you study DNF block, that's when you can connect coordination compound. Once you study coordination compound, you can connect with DNF block, isn't it? My god, 90 percentile, 99 percentile. If you want to get in chemistry, you will have to get around 70 to 72 marks. Yes, and guess what, from these two chapters alone, just from these two chapters, guys, you will be able to get around 16 to 20 marks. So isn't that great, everybody? Where is digital board? Bachu, garib teacher, I do not have digital board and all. If you want, you can sponsor it. I think one digital board costs around 5 lakhs. Sure, go ahead, sponsor it. I'll get it in my home. Okay, thank you, everybody. So quickly go call up your friends and let us start with the session. Before I start with the session, let me tell you all that this is the schedule of 21st December to 23rd December. Today at 6 o'clock, you already watched Shreyas sir live. Those of you who haven't seen his video, please go ahead and watch it. Once again, modern physics is one of the very high weightage topic, guys. Very high weightage chapter. You don't know this, you are basically letting go of a lot of free of cost marks in JEE. Okay, so do not let go of that. Now at 9 p.m. right now, right here, I'm taking the session, everybody, and finally on 22nd of December, that is tomorrow, limits, continuity and differentiability will be done by Nabamita Ma'am. All right, yes, everybody. Okay, love you too, guys, love you too, thank you so much. And Saturday, this Saturday, 23rd of December, 11 o'clock in the morning, we will start with a PYQ marathon, basically sort of one by one we will all take sessions. Okay, and one more thing, everybody. Now, since you are all a part of the session, part of this channel, let me tell you all that this is going to be a serious sort of studying, everybody, and we need to be really serious because we have only 1 month, right? So all I want you all to do is just a little bit of time. That is just below this description box, just below this video, in the description box, you get a Telegram channel link. Just go and join this because that's where I will be giving you the notes as well. So alrighty, everybody, are we all ready? Are we all ready with a pen and a notebook? Because I need you all to write down. We are also going to solve a lot of PYQs, solve some questions with the theory. It will be great if you have the pen and paper. Alright, now, so let us start first with my favorite chapter, that is coordination compounds, everybody. Yes. Okay, so coordination compound. The moment we say coordination compound, a lot of us, we do not understand and we think that, oh my god, this is going to be very complex. But that's not the case. First of all, coordination compound always had existed in front of us. We were just not able to understand it, right? Yes, so now coordination compounds. Let me give you a very simple example. Chlorophyll. You have heard about chlorophyll since beginning of time, isn't it? So chlorophyll is a coordination compound. Yes. The hemoglobin. Hemoglobin is also a coordination compound, which you all know, right? Now, to understand the definition, what we say is that combination of two or more stable compounds in stoichiometric ratio forms either a coordination complex, or we say that it forms a double salt. What does it form? It forms a double salt. Now, something that must be very, something that must be very confusing is that, ma'am, what is this double salt now? What is the difference between a double salt and a coordination complex? Let's talk about it. Okay, let's talk about it. So first of all, let us write that coordination compound, or even before coordination compound, let's just write one sentence here, and that is that combination of two or more, okay, combination of two or more stable compound, right? Two or more stable compounds in stoichiometric ratio, everybody. In stoichiometric ratio is called as, stoichiometric ratio gives us a double salt, or it can give us a coordination complex, right? It can give us a coordination complex. Now let us try to understand this. Let us try to understand this with some examples, everybody. Shall we do that? Yes. Shall we do that, everybody? What is a double salt, guys? Double salts are basically those salts. For example, let's take something called as carnallite, okay? Something called as carnallite. Now, what is the formula of carnallite? Anybody knows it? Anybody, guys? Anybody? Yes, can somebody tell me what is the formula of carnallite, everybody? Come on, guys. Come on. Yo, come on. Anybody who can tell me what is the formula of carnallite? Yes, can you guess? It's there in your NCERT if you haven't studied. Yo, you have to study anyway. The formula of carnallite, everybody, is KCl dot, yes, KCl dot MgCl2 dot 6H2O. Now 6H2O, everybody knows that's called as water of crystallization, correct? So now what happens is this carnallite, let's say that we put it in water, right? When we put it in water, we will see that all of them will dissociate into simple ions and they will get completely dissolved in water. Yes, so the moment you dissolve it in water, K plus will say yes ma'am, Cl minus will say yes ma'am, Mg will say yes ma'am, Cl2 will say yes ma'am. All of them are going to show their true colors when you dissolve them. Understanding this much? Very good, Sai Teja. Very good, Vaishnavi. Yes, do we understand this, everybody? Right. What did I say? I said that they dissociate into simple ions. Okay. Have a look. They dissociate into simple ions. Okay. Dissociate into simple ions. Simple ions completely and completely dissolve in water. Okay. Completely dissolve in water. Clear? This much is clear, everybody? Great. Now what happens is, now let's say that if I take a complex ion, let's say that if we are getting a coordination complex, now what? Now what will we get? Okay, have a look. Let me take another example. Okay, and this time I'm taking an example of a coordinate complex, that means K4FeCN6, let's say. Now when I put this in water, do you know what will happen? Do you know what will happen? What will happen is this will dissociate. So we will get K plus. But this Fe and Cn minus ions, we will not be able to see. Yes, they will not dissociate. This compound, it will not dissociate into Fe plus 2 and Cn minus ions. Are we getting this? Yes. Are we getting this, guys? Do not dissociate into Fe plus 2 and Cn minus ions. Alright, this much is clear. So this is our introduction towards coordination compound. Cool? Alright. Now let us understand some of the terminologies which are very important. First of all, coordination entity or coordination sphere. What does it mean? The coordination sphere or coordination entity means, guys, do you see, everybody? Okay, let me write this once again. Okay, let's say that K4FeCN6, right? This is what I said, isn't it? So this whole thing, everybody, this whole thing, if you see, this will be called as your coordination sphere. What will be this called as? This will be called as a coordination sphere, alright, or a coordination entity. Basically one and the same thing, okay? Alright, now what about the central atom? central metal atom, guys, the central atom or the ion is supposed to be a metal, and right here, as you all can see, Fe, that is iron is our central metal atom right here. Can you all see, everybody? Right here, can you all see? Great. Okay, all right. Finally, what happens is we have another term that is called as ligands. What is a ligand? Ligand is these CN right here. Yes, ligands can be neutral molecules, ligands can be anions, ligands can be cations, which are directly linked to the metal atom, directly linked to the central metal atom or the ion in a coordination entity. Okay. Further, we will talk about this cationic ligand or anionic ligand and neutral ligand. We will talk about this. Don't worry about it. Okay. All right, guys. Now, moving on. Something that is called as coordination number. What is coordination number? The number of ligands that are attached. For example, right here, do you see that there are 6 cyanide atoms that are linked to this Fe? So, what will be the coordination number? 6. Very good. Yes, very good. 6 is the coordination number. All right. There is something called as oxidation number as well. What is this oxidation number? Oxidation number is the charge on the central atom if all the ligands are removed. Now, you have a coordination entity or a coordination sphere. If you remove all the ligands, then what is the charge that the metal atom has? That will be equal to your oxidation number. And there is a formula that we use to carry it. Okay. All right, everybody. Very good, Vaishnavi. Guys, let the chat go on. Let the chat go on. Yes. Keep telling me whenever I'm asking you a question. Okay. Yes. Whenever I am asking you a question, you guys will have to let me know the answer. Yes. Everybody be active on the chat box. Don't go. Don't go. Be active. I hope that you all had your dinner and everything, right? Did you all have your dinner and everything? You had? Okay, great. Chalo. All right. Now let's talk about the classification of complexes. The complexes, the coordination complex can itself be, yes, the coordination complex itself can be cationic. What do we mean by cationic? What charge do we mean? Cation means it has a positive charge. Yes. For example, have a look. Cr, that is chromium, and then NH36, and here there is 3+. I'm not talking about the nomenclature yet. I'm not telling you what name should we give it to the complex, because we will go easy peasy biryani tasty. Everybody, whenever you understand in my class, what do you write? Whenever you understand something in my class, what do you say? Hashtag EPBT. Okay. Yes, you will be saying hashtag EPBT. Yashwan, don't worry about it. I will be teaching chemical bonding after this. Okay, coordination and DNF block are the most high weightage. After this, we will be doing chemical bonding. Yes, okay. Yes, PDF of the class will be provided in the Telegram channel. Don't worry about it. Yes, yes, yes. No problem, Death Stalker. No problem. Yes, very good, Luxury Hitler. Very good. Okay, so whenever you understand something, what do you write, guys? Hashtag EPBT. Yes, hashtag EPBT. That's what you write. Great. Okay. Now moving on, everybody. What if the complex has a negative charge? That means it has a net negative charge. What if it has a net negative charge? What are we going to call it? Absolutely right. Yes, we are going to call it as a anionic complex. For example, you can see here FeCN6 3-, because it has a 3- negative net charge. This will be an ionic complex. Great. Now, there are also complexes which are neutral. Yeah, they do not have any charge. Come on, they don't want to. So, nickel with CO has no charge right here. We call this neutral complex. Then, there are something called as what? Homoleptic. The moment you hear homoleptic, what do you understand? Homo means same, right? Yes, homo means same. That means that all the ligands that are attached to the central metal atom in the coordination entity are supposed to be same. Right? So that's your homoleptic. If there is a homoleptic, that means there has to be also a heteroleptic complex. Absolutely. So what is a heteroleptic complex? A heteroleptic complex is basically when there are more than one type of ligands attached to the central metal atom. Righto? Perfecto? Understoodo? Great. Now, let's solve a question, everybody. So, chalo. Let me show you now how to calculate the oxidation number, everybody. Does anybody know how to calculate the oxidation number? Yes, Sudhakar, what are you asking? What are you asking, Bacha? I haven't seen your question. Please tell me. Yes. Yeah, we will do separate section. Yeah, haven't Shreyas sir has told you, no, yesterday in the 9 PM session that there is a PYQ session that will be separately done. Tarun, I am not going to do organic chemistry. Organic chemistry will be done by Pahul sir, and he will be also taking class. Oh guys, come on, didn't you see yesterday's launch? Didn't you hear all the details of, series and everything that Shreyas sir has told you? I think he has told you all of these. Anyway, come back guys. So how do we calculate oxidation number, everybody? All we have to do is, we calculate the oxidation number of the metal, right? Yes, we calculate the oxidation number of the metal. Here our metal is nickel. So let us say that this is our X, okay? Now this C2O4, okay? Everybody have a look. C2O4 is called as oxalato ion, all right? Yes, and we know, I know, and I'm guessing you also know because you have studied this, right? For some time and many times, right? So you probably do know that this has -2 charge. Oxalate ion has -2 charge. Now there are 3 oxalate ions, so plus 3 multiplied with -2, and here everybody, do you see the overall charge, guys? The overall charge here is -4. Great. Yes. So what do we write? Is equal to -4. Now calculate this. What will you get? X plus 3 to the power -2 is 3. Multiplied with -2 is 6. This is equal to -4. So X is equal to +2. That means EPBT, option number C for Capto. Yes, C for Captain. That is your correct answer. Very good. Very good, everybody. Chalo, moving on. Let's go. Now, let us take a look at the classification of ligands, guys. Okay. Now, ligands can also be of different types, obviously. Complexes, if complexes are of different types, how can we say that ligands are of ligands are of also different types? So now we can, on the basis of charge, we can differentiate ligands such as neutral, positive, negative. Neutral ligands are such as amine, NH2, aqua, H2O. Aqua bole to water, na? Everybody knows. Do I have to explain that? No, I guess. Yes? Please explain it again. Which one? What? How to calculate oxidation number? Just go back and watch it, bacha. It's very easy. Yeah? Very easy. EPBT full form is easy peasy biryani tasty. Because I love biryani, so we do not say easy peasy lemon squeezy. We say easy peasy biryani tasty. Okay? Okay. Alright, everybody. So ligands, neutral ligands. Do we understand what is neutral ligand? Water is a neutral ligand. Okay? NH3, amine, is a neutral ligand. They do not have any charge on them. Now, coming to positive ligand. So there are positive ligand like NH2, NH3. This is called as hydrazinium. Please make a note, everybody. Do you see EM at the end? Do you see EM at the end? We did not have that in the neutral ligands. Do you see? In aqua or amine, we did not have something like EM at the end, right? We did not. Exactly. NH2, NH3 together is a ligand, and that is called as hydrazinium. EM. I'll tell you more about that. Don't worry. Yes. Now, negative ligands such as Cn minus, OH minus, these have negative charge. So, negative ligand. Cool. Now, based on denticity. What is this denticity, Baba? Denticity. Chalo. Let's understand this denticity a little better. Okay. Denticity. Dent. Dent, do you all understand? Don't you all go to dentist? What do a dentist do? Teeth, right? What do you do with your teeth? Chew or hold on to something, right? Most of the animals, you must have seen that whenever they're hunting, they're holding on to something with their teeth, correct? In this case, the ligands have basically claws or teeth with which they can hold on to the metal, right? So if a ligand can hold on to the metal with just one single teeth, it will be monodentate. 2 teeth, bidentate. 3 teeth, tridentate. 4, tetradentate. 5, pentadentate. Let's not go more. We can just call it as polydentate. Understood? Yes. Understood, everybody? Do we understand, everyone? Correct? Great. So, based on the types of ligand, let me now give you some examples as well. So, bachalo, by the way, everybody, all the bachus, please try and understand that today I am not going to do a lot of handwritten stuff here, because I'm taking 2 chapters, both the chapters. If I have to really diligently teach you, both of them together will go for at least 12 hours, which is why most of the things are written, so that I can just explain to them and I can underline them and I can highlight them. Does that work, everybody? Does that work? Great. Now, so monodentate ligand, everybody have a look. Monodentate ligand. So I said that they can hold on to the metal with one single teeth, right? Now, understand it. Chemistry, right? One single teeth becomes very vague. That does not really happen. Correct. What happens is this ligand, which I just said that it will hold on to the metal with one teeth, actually it's not a teeth. Actually, it's a donor atom. Okay, what is it? A donor atom. There will be one atom in the ligand which is able to donate electron to the metal atom, and that is your monodentate ligand. Now, have a look. So, they have one donor atom. Now, have a look. H2O. H2O has only one donor atom, and which is the donor site, everybody? The donor site is oxygen here. For NH3, nitrogen is the donor site. For Cn minus, C, carbon is the donor site here. F minus, only one atom. F minus, where is the other one? Nothing is there. So monodentate. Cl minus, 1. Br minus, only one. So all of these are monodentate ligand. Understood? Oh, perfecto. Everybody clear? Oh, yes? Great. Moving on now. Then we come to bidentate ligand, everybody. So this bidentate ligand, remember what I said? Two teeth. But obviously it's not two teeth. It is going to be what? It is going to be two donor atoms, right? Two donor sites. Bole to, have a look. Oxalato. Oxalato. Yes. In case of oxalato, you see here there is a donor site and here also there is a donor site. By the way, I just said that Cn minus, carbon is the donor site. It's actually nitrogen. Nitrogen is the donor site. Sorry for that mistake. Nitrogen is the donor site here, guys, not the carbon. Okay. Moving on, everybody. Oxalato. In oxalato, do you see this oxygen and this oxygen? Both of them can hold on to the central metal atom like this. Understanding? Great. Okay. And similarly, you have another example that is called as ethylene diamine. Ethylene diamine in your exam will not be written completely. It will not be written as ETHY. Nobody has so much time. It will be written in bracket EN. That's it. If you see EN, don't think like, oh my god, what is this ligand? I don't know. EN is ethylene diamine. It's a bidentate ligand. Understood? Yes? Understood, everybody? Great. Moving on. Now we come to tridentate ligand, guys. And the tridentate ligand here will have obviously three donor site. This is diethylene triamine. What is this? Diethylene triamine. Alright. So now you get the gist of it, right? You get the gist of it, everybody. So let's go a little fast. Then tetradentate example is triethylene tetraamine. This will be written as tri-N. Okay. Pentadentate, you have ethylene diamine triacetato-ion. This does. You are asked a lot of times about EDTA in your JEE paper. So please have a look at it and make a note of it. Okay. Alright. Then we come to hexadentate. Hexadentate will obviously have 6 donor sites, right? And this one, everybody, is now. Have a look, everyone. Don't get confused. EDTA with 1 negative charge is pentadentate. EDTA with 4 negative charge is hexadentate. Yes. Alright. If you have any doubt, you can ask in the comment section after the class is over. We do go through the comments and I will definitely answer. Okay. So ethylene diamine tetraacetate ion EDTA 4 minus is a hexadentate. Now let's talk about ambidentate. What is ambidentate? Have you heard about okay, I always give you this example. How many of you have watched 3 Idiots movie, everybody? How many of you have watched 3 Idiots movie? Have you guys watched 3 Idiots movie, everyone? Yes? Yes? How many of you have watched 3 Idiots movie? How many of you have? Come on. Guys, Meghna, all that we don't know. We are not astrologer. We will see what happens. We will see. How many of you? Anushka has watched? Yes, Anushka has watched. Anybody else who has watched 3 Idiots movie? Now, in 3 Idiots movie, have you seen Boman Irani? Boman Irani, right? Now, Boman Irani, what was his name? Professor Sahastra Buddhi or something his name was? Yes? Professor Sahastra Buddhi or something like that his name was. Now, have you noticed that he could write with both his hands like this? Yes? Yeah? Have you noticed? That fellow used to not sleep also. He used to only sleep while shaving his beard. Shastra, exactly. So a person who can write with both the hands, you know what you call them? You call them ambidextrous. Do you remember? Ambidextrous, you call them. So similarly, you have to remember this, guys. You have to remember this. Ambidentate means a ligand which has two donor sites. By the way, this ligand will only use, at single point, it will only use one of its donor sites. That means it has two donor sites, acts like a monodentate ligand, but can hold on to the metal with either this hand or that hand. Understanding? Understanding, everybody? What I'm trying to say? Yes? Virus, coronavirus is again coming, by the way. Wear your mask and don't go out. Sit and study at home. Yes. So, for example, the best example of this is, everybody, remember sometime back, what did I tell you? I told you that I made a mistake. Actually, N minus is the donor site in Cn minus. What happened there? I did not make a mistake. I did not make a mistake. So many of you thought that I made a mistake. No. First, I told you that carbon is the donor site. After some time, I said, no. Actually, N minus is the donor site. But now, come back to it and see that both of them are donor site. But at a single point, they will only be using one of the donor sites. So example, Cn minus, ambidentate ligand, NO2 minus, ambidentate ligand, SCN minus, ambidentate ligand. In case of SCN minus, either it can use the S hand or it can use the N hand and then hold on to the metal however it wants. It can use both the hands however it wants and it can bond to the metal. Cool, everybody? Do we understand this? How many hours? But I think we will be finishing the sessions by 11:30 or so. Yeah, 2.5 hours I'll at least need to complete 2 chapters, right? Yes. 2 chapters probably, right? No, J is not getting postponed. Don't worry. Now, guys, something that is very important, everybody. Please listen to me. What is called as chelating ligand? Again, listen to me very carefully. Chelating ligand. It only happens with बड़े-बड़े शहरों में छोटी-छोटी बातें होती रहती है. No, it only happens with a polydentate ligand. Yes, polydentate बोले तो bidentate, tridentate, tetradentate, hexadentate, whatever. Polydentate ligand. It has to have more than one teeth. Okay, has to have more than one teeth. A polydentate ligand. Now, understand this, everybody. Okay, have a look. So let's say that. Okay. Do I have anything else to? Okay, yeah, I do. So let's say that this is my chashma box, right? This is my specs box. And let's say that here I have these three, okay? These 3 fingers, this your sign we make, right? These 3 fingers I'll be using to hold on to the metal. Now, if you look at it carefully, do you see that it's like a ring structure that I'm forming here? Do you see that it's like a ring structure that I'm forming here? Cancel everything else. Do you see that it is like a ring structure? Exactly, that is what is called as a chelating ligand. But choose. Understood? Easy peasy biryani tasty? Write it down in the chat box. Write it down in the chat box. Easy peasy biryani tasty? Yes. Now read the definition. When a polydentate ligand is bonded with metal atom from one or more donor side, then the resulting structure is a 5 or a 6-membered ring. Then the ligand is known as a chelating ligand. Do we understand this? What are you asking, Yenduru? What? Sai Pramod. What are you asking? Please, what? What are you asking? I don't know what you're asking. Yes, everybody, easy peasy biryani tasty, right? Do we understand this? Great. Chelating ligand, we have understood. Great. Okay. So a question. Now tell me, this following ligand, what is this? This is a hexadentate, tetradentate, bidentate or tridentate. Come on, guys, let me know, everybody. Till then, I'm going to drink some water. Everybody, you know, let me know the answer. Guys, the session, I do not know, but mostly we will be ending the session by 11:30. Okay? We will be ending it by 11:30. Sai Pramod, I do not see what you are asking. What are you asking? Surbhi, I think I just answered you. Yes, guys. Anybody? Anybody? B. Very good. Very good. Chalo, let's check it out. See, here you have one oxygen here. Here you have one oxygen. So this can donate. This can donate. This nitrogen can donate. And this nitrogen can also donate. So once again, everybody. 1, 2, 3 and 4. That means what is this? This is a very good option B. Tetradentate ligand. Yes, this is a tetradentate ligand. Cool. Alrighty. Moving on, everybody. Now, let's have a look at nomenclature. I was saying nomenclature. Yes. Will you not sleep? We will sleep. But right now, don't disturb. No, listen to the class. The more you talk to me, the more the timing will get stretched. Shh. Just keep writing EPVT and only ask me doubt. Okay? Don't question all of these things. Otherwise, the session will keep getting delayed and delayed. So, shh. Yes. Now, everybody, stop asking this. How much time will you take? How much time? Why do you want to be astrologist? Just sit and study. You guys, chalo. Now, everybody, come back to me. Come back here. Come back. So, let's understand the rules to name a coordination compound. You know, in your general organic chemistry, you read about nomenclature, isn't it? Yes. In organic chemistry also, you have yes, Nani, that is why. That is exactly why. Yes, I will send you the PDF. Yes, absolutely. Everybody, shh, guys, so much disturbance here. Now, how do you name a coordination compound? Number one rule is that you will always name the cation first. Yes, doesn't matter if your coordination entity is positive or negative. If the coordination entity is negative, then you write the counter ion first. Now, let me give you an example here. Understand this, everybody. So, let's say that you have K4 FeCN6, isn't it? Understand it. This is my counter ion. This potassium is my counter ion, right? So this is my cation as well, because we always know KCl. What happens when KCl breaks down? What do we get? We get K plus Cl minus, right? What happens when you have NaCl? Na plus Cl minus. So what are these? These are cations, correct? So that means here also, when this will dissociate, you will get a cation here, and the whole of coordination entity will be negatively charged. So that means this time the coordination entity is an anion. Now tell me, which one are we going to write first? We are going to write the name of the cations first. So we will start with potassium. We will start with potassium, and then we will go on and write down the name of the coordination entity. That I will tell you in some time. Okay. Now come back, everybody. Now, what you do is, before you write down the metal atom's name, you write down the ligand's name. And how? What order will you follow? You will follow the alphabetical order. Absolutely right. For example, now if you have two ligands, let's say you have H2O as well as NH3. What will you do? If you have NH3, which is amine, and you have H2O, which is aqua, now which one will you choose? AQ comes first or AM comes first? AM comes first, right? AM comes first, and that is why you will write amine first and then you will write aqua. Okay? Alright, everybody. Alphabetical order. Cool. Yes. And we will not take a look at the prefix, by the way, because you know, Chalo, we will come to that later. We will come to that later. So before the name of the central metal atom, you will write the ligand. For example, here what will happen is, I have written potassium first. After writing potassium, now here I have only one sort of ligand, right? One kind of ligand. So what am I going to write? I'm going to write hexacyano. Hexacyano. And then I will write the central metal atom. Okay? But why did I write cyano here? But we know it is cyanide, right? I could have written cyanide. Why did I write cyano here? That we will come back to it. Chalo. Now what happens is, now have a look. See, anionic ligand. If you have an anionic ligand, that means the ligand carries a negative charge. Then you are going to put the suffix O. For example, chlorido. Yes, chlorido for Cl minus. You will write fluoro. You will write fluoro for F minus. You will write oxalato for oxalate ion. You will write cyano for cyanide ion. Getting it? Getting it, everybody? Yes. Well done. Now, if you have a cationic ligand, remember hydrazinium, I gave you an example, hydrazinium, NH2NH3 positive. Yes, that is why we write the suffix -ium, alright. If it is negative, O. If it is positive, -ium. Now, here what will happen is another example. Take another example. Let's say that you have NO positive. What is this called as? This is called as nitrosonium. What is it called as? Nitrosonium. Alright. And if you have a neutral ligand, nothing. It's all chill. All chill, everybody. Yes, okay. So now do you understand why did I write hexacyano? Yes, alright. Now what happens is, okay. So let's say that number of individual ligands. How many ligands are there? Did you also see that hexacyano I wrote? Why did I write hexacyano? Because CN6 was there. There was 6 CN, correct? There was 6 CN, hence I wrote it as hexacyano. If there were only 4 CN, then what would I have written? I would have written is as tetracyano. Getting my point, everybody? Getting my point, guys? Yes? Okay. So if it is 1, mono, 2, di or bi, you can write. If it is 3, then tri. If it is 4, then tetra. If it is 5, then penta. If it is 6, then hexa. After 6, you don't have any other because you can only get octahedral complexes, right? So you only can have a 6. Please detail it. Bacha, how much more detail are you asking me? CN is a neutral ligand. CN has a minus. It's an anionic ligand. CN minus. We write CN minus, okay? Yes. So somebody is asking me, Nani is asking me, I can't understand more detail. Guys, do you really need more detail in coordination compound? Because I do not think it can be more detailed than this. I'm literally at the end of the session. I'm still taking care of the nomenclature. Please tell me what help do you need, Nani Rupesh? What is it that you cannot understand? What is it that you cannot understand? Okay. Friends forever, it cannot be FeFeH2O6. Okay. There has to be something else. The counter ion will be something else. Okay. Yes. Okay, guys, moving on. Yes, we understood. Now. By chance, if the ligand itself has a di, tri something. Remember the examples that we gave you? Remember ethylene diamine. There was, right? Yes. Triethylene tetra something, right? If those are the cases, then do you know what you do? And that case, you do not use mono, di, tri, tetra. No. At that point of time, you're going to write bis, tris, tetrakis, pentakis, like that. Okay. That's how you have to name the compound. Am I making sense, guys? Hashtag EPBT, everybody. Thank you so much, Safir. Okay. Now, okay. This, please be careful, everybody. This, please be careful because you never know. This time, you still know that, right? That most of the 𝐕𝐞𝐝 chapters are poof, gone in thin air. Where will the questions come from? These high weightage chapters. They might ask you how to write IUPAC name. They might ask you for ambidentate ligand. So you don't know. Please pay attention, everybody. Pay attention. Now, if there is an ambidentate ligand, how do you write the name? Chalo, let's take example of pentachloro. Okay, chalo. Let's see that you have cobalt, CO. Yes, you have cobalt, then you have Cl5, okay, and let's say you have NO2, okay. Yes, if you have this kind of a compound, then now do you see that NO2, this particular ligand here, this is an ambidentate ligand. This has an ambidentate ligand, everybody. So now it can either be, let's draw the structures, everybody. So it can be cobalt here. Yes, you have 1, 2, 3, 4, 5 and 6, right? Yes, so it can either be Cl here, Cl here, Cl here, Cl here, Cl here, and let's say that it is attached like this, okay? NO and O. Or it can be CO 1, 2, 3, 4, 5, 6, right? So Cl, 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 and finally right here, let's say that it is attached like this. So now do you see? On one side, it is attached with oxygen. On the other side, it is attached with nitrogen. Right? Do you see that, everybody? If that is the case, now how do you name it? You name it as, my dear students. Please pay attention, everybody. Please pay attention, guys. Do not start asking questions about each and every chapter that I'm not teaching right now. Be at the present scenario. Do not spam, please. Spam, don't spam, don't spam. Stay here, listen to what I'm trying to tell you. So you can either write it as, for example, this, right? If I want to write the name of this compound, then I'm going to write it as pentachloro. Have a look, everyone. Now in this case, do you see what is this ligand? This is called as nitrito ligand, right? This is nitrito ligand. So I am going to write it as, within a bracket, nitrito. And the most formal way to write this name is introduce a letter called as kappa. Then write the element with which it is attached. Now this side, do you see N here? N is attached to the central metal atom, right? So you write N, close the bracket, then write cobaltate. Okay, this is actually, right here there should be a counter ion. So this has a negative charge, let's say. So I'm writing it as cobaltate. Okay, and then in the bracket you write down the oxidation state. You write down the oxidation state of the central metal atom. Okay. Now, if I have to write down the name of this compound, this one, then how am I going to write? Similarly, I'm going to write now pentachloro. Yes, I will still write it as nitrito because that's the name. We can't change the name. Kappa, but this time I'm going to write oxygen and then similarly cobaltate and oxidation state 3. Now, do you understand? Kappa. Kappa is a Greek letter. Like you have alpha, beta, gamma, delta. Like that, K is called as kappa. You have many, right? Epsilon, eta, mu, all of that, those letters. Exactly. So, kappa is also a letter. Okay? Kappa is also a letter which we introduce especially when we are writing ambidentate ligand. And this, my dear student, is the most formal way to write the name. There will be many other teachers who will be telling you a lot of other things, but this is the exact IUPAC official name how you write it. Okay? Cool, everybody? Pihu, atomic habits, kappa. Yes, kappa understood. AS understood kappa. Yes? Kappa, everybody understood. Why brackets? Because it will all get confused, na? Yes? Nitrito is getting attached either with the N hand or the O hand. If you write everything together, it gets very confusing. So IUPAC suggested that you have to put it in a parenthesis. Okay? These brackets are necessary only when you have an ambidentate ligand. Only when you are writing an ambidentate ligand, that time you need this bracket, not otherwise. Alright? Yes? Yes, Prithviraj? Understood? So, chalo everybody, hashtag EPBT. Hashtag EPBT. You call frog as a kappa. Kappa is necessary. Like I said, Pihu. This is the most formal IUPAC way to write it. Yes? Brackets are necessary. Baba, it's not my rule. It's IUPAC rule. Okay? If IUPAC has told you, they are the Bab, they are the godfather of chemistry. Write it down. In the end, you will lose some marks in chemistry in your exam. Then you will come back and told me that, ma'am, you told us not necessary. This is IUPAC, bro. Just write it. Maybe Mohit. You never know. You never know. There may be. It's not my rule. Had it been my rule, I would have said, chuck it. Exam only. No, chill. Right? Okay. Chalo. Alright, guys. Now, finally, last one is that oxidation state of the central metal atom. It should be written in the Roman numeral in parenthesis, everybody. What is parenthesis? Once again, bracket. Yes. So, bracket is necessary. When you are writing the oxidation state, bracket is necessary. Pihu, no. Cl is a single entity, right? Cl. It's one single element. If there are several atoms in a ligand, then you have to put it in parenthesis. Then you have to put it in bracket. Understanding? Then you have to put it in. So it's Cl2, not Cl2. Never. But it is NO2 It is not NO2 just like that. Are you getting it? Yes? So, this is right, this is wrong, this is wrong, this is right. Got my point, Pihu Jain? Got it? Got it? Chalo, moving on everybody. Now, I think this we have already understood, right? Acha, no. Complex, huh? Now, everybody, please pay attention. This you might feel like, but ma'am, this is repetitive. This is not repetitive. This is not repetitive. Everybody understand. Now, we're talking about the complex. If the complex, the whole ion, the coordination complex, everybody, is cationic, no suffix. But did you notice, everyone, that I wrote here cobaltate? What did I write? I did not write just cobalt. I wrote cobaltate. Why? Because that's the rule. If it is an anionic complex, then I have to write 8 as the suffix. So for example, let's go back to that example that we had, K4FeCN6. Now see, hexacyano. Now will I just write iron? No, I will be writing ferrate. What will I be writing? Ferrate, everybody. Why? Because this whole complex has a negative charge. Have a look. This whole complex has a negative charge. Hence, I'm going to write it as 8. Great. Okay. 8. Great. Okay. Now, moving on. If it is a neutral complex, nothing at all. Okay. Now, everybody, let's understand one more thing. Okay. So, there are certain times when we also have to use the Latin name of the metal. Okay. For example, if it is iron, then we know that what is the cation or the neutral name. What is going to be the cation or the neutral name? Anybody? Any idea, everybody? Oh, it has to be iron, isn't it? This is iron. Now, if it is an anion, then we write it as ferrate. This is exactly what I wrote now. Correct? If it is Ag, then Ag cation or neutral, it will be silver. But if it is an anion, we will write it as argentate. Gold. Gold in cation or neutral form will be gold, but gold in anion form will be aurate. Aurate. Okay. If it is Pb, Pb is lead. Lead in cation or neutral form is lead, but in anion form it will be plumate. Okay. Sn is what? Sn in cation neutral form is tin, but Sn in anionic form is stenate. Some more, everybody. Molybdenum. Okay. Molybdenum is, everybody, molybdate. Okay. Molybdenum is molybdate. Is NCERT enough? Enough, but there are certain questions that might come, everybody. Okay. Okay. There are certain things that you will have to pay attention to. Okay. So now let me give you a cheat sheet, everybody. This cheat sheet is very, very necessary. Here you will also get the name of the complexes. Here you also have the ligand, the formula. I will be giving you this whole PDF, everybody. I expect you all to just print this out, everyone. Okay. Just print this out and stick it right in front of your table, so that every day when you keep looking at it, at least the nomenclature here will be, what do I say? It'll be clear. Absolutely clear. Yeah? Okay? Chalo. Okay? I guess you got a headache trying to remember? No, bro. Have been practicing for such a long time. So no, not at all. I already have a 4+ years of teaching experience. You cannot have a headache right now. I mean, yeah, initial days, yes, very, very true, very true. Not now anymore. Okay, so everybody, till here, are we clear? Shall we start with the main movie, everyone, of coordination compound? Can I get some EPBT, hashtag EPBT, everybody? Can you all please tell me hashtag EPBT, everybody? Chalo. Hashtag EPBT. Gly is glycine. Glycine is a bidentate ligand, okay? Glycine is a bidentate ligand, everybody. Acha. Now, everyone, just have a look at your valence bond theory, NCERT, right? In your NCERT valence bond theory, everybody, do you know what they have said? I have it right here. So, let me read this sentence, everybody, okay? Just so that you guys understand. Please listen. It says, according to this theory, the metal atom or ion under the influence of ligands can use N-1D, NS, NP or NS. ND orbitals for hybridization to yield a set of equivalent orbitals of definite geometry. What do you understand? Nothing, right? What did you all understand, everyone? Did you all understand anything? You'll be like, what, ma'am? What is this? All of this, huh? No, can't understand. Sure, let's understand. Valence bond theory in chemical bonding chapter. We have read about valence bond theory. We have read in chemical bonding. And what do we know? We know that especially carbon. Remember, carbon, when it tries to form bonds with hydrogen, what happens? Hydrogen can only give s orbital, but carbon has certain bit of p orbital. So carbon will give some p orbital, hydrogen will give some s orbital, then sp3, there will be a hybridized. And now, do you remember that what it did was, in case of VBT in chemical bonding, we read that in all the orbitals, there were 1, 1, 1, 1, 1 electron. Remember? There were 1, 1, 1, 1 electron, so that the other electrons can come and join. But here, there is a twist. What is the twist? What do you think is the twist? Here the twist is very simple, very easy, everybody. Very simple, very easy. The twist is, you know what the metal will do? Metal will hybridize. It will try its best to bring all the orbitals to the same energy. Not all the orbitals, I mean the orbitals that are going to take part. Yes, they are going to bring it all in the same energy. Then the metal sees that, oh, the ligands are coming, and this time it is a coordinate bond. It is a coordinate bond, but choose. Coordinate means what? 2 electrons donate, 2 electrons daan, 2 electrons completely donated. So now tell me something, that here if the metal has 1, 1, 1, 1, 1 electron, 2 electrons from the ligand, where will they sit? On the head or what? No, that cannot happen. So are you understanding what has happened? So first thing that the metal does is hybridize, bring it all to the equivalent energy. Second thing that the metal will do is empty the whole thing. Empty the orbitals. The hybrid orbitals will be now emptied. Hybrid orbitals will be emptied. And then the metal will be like, ligand, take it and fill it with your electrons. Take it and fill it with your electrons. Then it will give it. Understood? 3 things, everybody. 3 things that the metal and the ligand are doing in the valence bond theory is hybridize, empty it, give it to the ligand to fill it. Now tell me, hashtag EPBT. Has anybody else told you like this? Now, otherwise, valence bond theory, death. Does it feel like that? Does it feel like this? Does it feel very easy? So let me just write 3 things here so that you always remember valence bond theory in coordination compound, everybody. Firstly, hybridize. Then what happens? Emptying of the orbitals happen. And then what happens? Filling by ligand. Filling by ligand. That's it. That's it. Now tell me it is EPBT or not. Great. Okay. Now everybody, once this hybridization happens, what are the different types of structure that we can get? Very simple, very easy. If the coordination number, okay, if the coordination number is 4, my dear students, what do you get? You get type of hybridization. What is the type of hybridization we are expecting? Type of hybridization we are expecting, and the structure that we are expecting, everybody. Yes, what is the coordination number? Type of hybridization, structure. Chalo. If the coordination number is 4, what is going to be the type of hybridization? Easy peasy, biryani tasty, sp3 hybridization. What is structure? Structure is going to be, array, you guys are seriously pandus now, huh? Tetrahedral. This will be tetrahedral, right? Come on, you all know this, everybody. Acha, now if I have another, let's take another set. Yes, another set. Coordination number 4, but I say that the hybridization now is dsp2. Now what are you going to get? Now what are you going to get? Kahani mein twist. This is square planar. What is this? This is going to be square planar, right? Okay, works. Acha, that's it. Now that's it. Acha, now if I take coordination number 6, then what can you get? No, you will always get octahedral. No question, no doubt. This will always be octahedral, but the hybridization can be different, guys. Hybridization can be D2 sp3 or it can be sp3d2. Now we will understand that one of this is called as inner orbital, what is it? Inner orbital, and the other one is called as outer orbital. Right, everybody? Yes. Okay. So now everybody understand. Let's go, guys. So you can have inner orbital complex or outer orbital complex. What does it mean? What do we mean by this inner orbital complex and outer orbital complex? When we say inner orbital complex, guys, have you noticed here D2sp3? That means that right here we are taking the inner d orbital, that is n-1d. When we are taking this n-1d, it is going to be inner orbital complex. But when we are taking the above, the one ahead of n, when we are taking the outermost empty d orbitals, then we call it as outer orbital complex. Clear? Yes? Clear? VBT is not hard, Pihu. VBT is not hard. If you have just understood what I have told you, then it is going to be very simple, very easy. Now, in coordination number 6, octahedral, everybody have a look. So you have sp3d2, where nd orbital is used, right? I have just told you that. If it is nd orbital, then it is going to be outer orbital complex. Yes. And if it is n-1d orbital, then it is going to be inner orbital complex. Now, inner orbital complex, they have a low spin complex. Spin matlab, you understand, right? What is spin, everybody? What is spin? Spin is what? Spinning, this spinning. If it is low spin, that means I will not be able to rotate like this. If it is high spin, then easily like this I will be able to spin. Correct? Right? Very good. Okay. So that means if it is low spin, that means that there are 2 electrons in the orbitals. So they are not able to spin properly. If it is only 1 electron in the orbitals, that means they are very happy. They have more space. They will be jumping around and spinning. So high spin complex. Do we understand? Bachu, I have told you already that Pratik sir is teaching in the topper pod. He is in Vedantu, but he had to take care of the topper pod, and that is why Shreyas sir is back, right? You have Shreyas sir, everybody. Yes, I've just replied. Yeah, everyone, did you understand this? Did you understand this, guys? Now, I just told you that low spin, that means that there are 2 electrons in each orbital. If there are 2 electrons, nobody is unpaired. If nobody is unpaired, then what do you get? Diamagnetic. But if you have unpaired electrons, then what do you get? Paramagnetic. Please tell me that your VBT is now made simple. Is there anything else that you want to know about VBT? I guess that everything has been completed in VBT. There is nothing that we have left. Please tell me #EPBT. Achha, by the way, let me also give you one trick, okay? Let me give you a trick here, everyone. I think you'll thank me. Remember always D0, okay? D1, okay? D2, and if you have D3, okay? And if it forms a D2sp3 hybridization, which it will always, mostly it will always form D2sp3 hybridization. This will be inner orbital complex. Whenever you see that the metal is in D0, D1, D2, D3, it will form inner orbital complex. This is a trick. But if you have D7, D8, D9, okay, and D10, then what will you do? The ligand does not have space only. It does not have enough space. What will it do? It will try to take the hotel room also. Or it will try to take the guest room that you have also. So what will it form? It will form outer orbital complex, that is sp3d2. This will be outer orbital complex. Clear hai? Say clinical clear, everyone. Clinical clear. Yes? D7 will be sp3d2, na bacha? No, I'm talking about octahedral complexes. Pihu. Octahedral complexes, bacha. If it is octahedral, then it has to be sp3d2. I'm not talking about tetrahedral complexes. I'm talking about octahedral complexes. In case of coordination number 4, you get sp3 hybridization and you get dsp2. Tetrahedral only has coordination number 4. Octahedral has coordination number 6. Understood the difference? Yes. Okay. Now, shall we go to, what is it? Crystal field theory. Shall we go to crystal field theory, everybody? Yes? They can get excited in D7. What are you saying, Pihu? Pihu, have I explained it? Give example. And there are a lot of examples that will come. But if I keep taking examples, see, it's already 10. We also have to finish D and F block. Yeah, we will solve some questions, plus we will do the PYQ session. At that time, we will try and look at more examples. Okay, but I think I have taken coordination compound many times, everybody. If you are still not able to understand, do you mind watching the previous session once if you really want it in that much detail? Because if I have to get into that much detail, trust me, just coordination compound will take at least 7 hours in detail, thoroughly. 7 hours at least for this chapter. And then D and F block, again we will have to give another 4 hours. So that will be what? 11-12 hours. Can't do that now. 11:30 I also have to sleep, guys. I actually sleep by 10 o'clock, but today got it? Okay. We will do isomerism, Janu. We will do isomerism. Don't worry. Chalo. Acha. Now we go to crystal field theory. Acha. So in VBT, what did we say? In VBT, okay, there were disadvantages of VBT, right? We understand that VBT obviously had certain disadvantages. What was the disadvantage? First of all, VBT could not talk about magnetic nature of coordination complexes. You know what VBT do? VBT found a loophole and it used to calculate whatever calculated theory we know, then it says that see, it explains, see, it explains. That's what VBT did. VBT found a loophole, whatever was the calculated Bohr magneton, that it tried to stick it and said that, oh, it matches. So that was a disadvantage, right? We don't want a theory which is not able to predict the magnetic nature of coordination complexes. How can we use it? We cannot use it. Which is why we had to come up with another theory that is called as crystal field theory. Now, crystal field theory, what crystal field theory did was, that is also very weird and abrupt. Crystal field theory says that metals, take the metals as positive. Yeah, metals should be positive. Okay, and then it said ligands are anionic point charges. And then it says, so the metal and the ligand has an ionic bond. Okay. We agree to it. Now here you can see that there are certain postulates that I have written, which is actually given in the crystal field theory. In crystal field theory, the postulates are, see, the first one I said, right? The metal and the ligand bond are ionic only. They are purely electrostatic interaction. Why? Because metal is positive and ligand is anionic. Yes, ligand is anionic, right? Ligand is anionic, correct? Now, they say, in crystal field, they say the ligands are treated as point charges in case of anions or dipoles in case of a neutral molecule. If you have a neutral molecule, then it is considered to be dipole. If it is anionic, then it is a point charge. Okay? Next, it says that 5d orbitals in an isolated gaseous metal atom, they have the same energy. Okay, this we agree. This is absolutely right. Okay? This is absolutely right. Okay. Then it also says that because of unsymmetrical field of ligands, the degeneracy of the d orbital is lost and then it causes splitting. Okay. And the pattern of the splitting, it depends upon the nature of the crystal's field. Okay. Chalo, we will understand this now better with a story. This is a story time, everybody. Now, let's say that you have a family of 5, okay? Let's say that there are 3 siblings, mother, father, okay? So, mommy, daddy, and you have 3 siblings. And now, let's say that somebody is coming to your house. You suddenly hear after that, after you have, let's say that you kept the call and everybody is excited that, oh, guests are coming. Before that, all the 5 people, okay, let's understand this way, everybody. All the 5 people in the family, let's say that they were degenerate, okay? That means they had very little energy. They did not have energy, okay? They did not have energy. Now what happened was, suddenly they heard that, oh, guests are coming. So what happened? Everybody got a little excited. Everyone was excited. So now you have all the 5 orbitals or all the 5 family members are here. Now after some time what happens is, now you have those relatives which are like, beta, why are you not studying? Beta, why your JEE mock tests are not better? Beta, how are you doing so worse in your mathematics? That happens? That happens? Correct. So now let's say that it's not your those relatives. It is, let's say, the relatives have come, and the relatives are such that they only throw taunts at your parents. Okay. So now what happens? Now you are all here, everybody. You are all here. This is the whole family member, everyone. Now what happens? Your parents get to know that, oh, these relatives are those ones which only taunt us. So the parents, they are now even more angry. They're like, why are they coming here? What will happen to us? What will happen to us? But you are like, oh, those people, they're not going to disturb us. So what happened? Your energy, it came down here. So you are 1, 2, 3, you are here. This point is called as barycenter. This is called as barycenter, everybody. Okay. And this is your T2G and this is your EG. Now you're going to ask me, ma'am, why are this GG here? G is actually a German German letter called as Gerard. Okay. What is it? Gerard. Gerade. This is present when there is a symmetry. So in octahedral complexes you have symmetry, whereas in tetrahedral complexes you do not have the symmetry, which is why in tetrahedral complexes we write it as T2 and E, but here we write T2G, EG. Understanding? Understanding? So now the parents' energy has gone up. They are like, why are they coming? No, we're not liking it. But the parents, the energy of the parents went up from the barycenter. In compared to who? If you compare the energies, then in comparison with whom did the energy go up? These three, isn't it? In comparison with these three orbitals, the parents' energy have gone up. So can I write it here as 3 by 5? I can, right? And your energy, the siblings' energy have come down compared to, yes, those two parents. So 2 by 5. Agreed? So this is the whole diagram that we usually make. Okay? This is the whole diagram that we usually make. Do we understand this, everyone? Do we understand this, guys? Yes? My concept, no. This happens. Okay, what if your parents don't like those uncle and auntie? Then they will get angry, no? Then they will get angry, no? Huh? Especially haven't you seen, if father side somebody is coming, mom gets angry like, why is she coming? She will find flaws in my cooking. She will find flaws in what I wear. They get angry, no? Anyway, alright guys, moving on everybody. Yes, moving on. Chalo. Now everybody have a look at this. Now do you understand what is happening here? So everybody, you have 5 orbitals, right? What are the 5 orbitals? dxy, dyz, dzx. Dzx, dx square minus y square and dz square, right? So these are the degenerate right here. See, these are the degenerate. Their energy is low because they're not doing anything. This is just a normal day-to-day life and they're fine with it. They're following routine, nothing to get excited. And then what happens? They hear that, ooh, ligands are coming and they're going to hit right on the head. So what happens? Their energy goes up. After some time they realize that, oops, it's only the ligands are going to hit. Acha, now everybody, do you all know these 5 orbitals? You have non-axial ones and you have the axial orbitals. Which are the axial ones? Dx square minus y square and dz square. These are the axial ones. Because, okay, everybody, have a look guys, have a look everyone. I'm pretty sure you know. So this, if I make this, see, this is what? dz square, right? This is your dz square. See, on the axis. On the axis. So this is called as axial orbital, right? This is your axial orbital. And if I draw it like this, here, here, here. What is this? Is it falling on the axis? No. This is your non-axial. Now, so the non-axial ones are, oh, this is not coming and hitting on our head. So they are like, oh, cool, we will settle down. But the axial ones, they're like, my God, the ligand is going to come and hit right on our head. So their energy went up. And exactly similar thing is written. See, delta octahedral splitting here 3 by 5. As you go down, delta octahedral splitting 2 by 5. Understood? Is this clear, everyone? How the splitting has happened? Do we understand, everyone? This is clear. Crystal field splitting, everybody understood? Now, crystal field splitting obviously depends on certain factors, right? What are the factors? If it is a weak field ligand, the splitting is not going to be so much. If it is a strong field ligand, yay, it is going to be so much. Like, see, again, understand with the story, everybody. Understand it with the story, everybody, that if you are, let's say that, okay, there is some distinct relative whom you do not know properly. That relative, are they going to excite you so much that, yes, somebody is coming, yes, somebody is coming? No. Probably they are not even going to bring you any gifts. So you are not bothered at all, right? So if it is a weak field ligand, then the splitting is not going to be so much because the orbitals understand that it's okay, right? Isn't it? But if it is a strong field ligand, somebody who you know, if it is your cousins, you're going to be very excited, like, oh my god, I'm so happy my cousins are coming, we're gonna have a lot of fun, we're gonna watch movie, we're gonna have ice cream, we're gonna have this, that. You're going to be super excited, right? Exactly. So a strong field ligand, more splitting. Weak field ligand, less splitting. If it is a weak field ligand, weird colors. Strong field ligands, great colors. Now colors also we will talk about. Yes, so everybody understanding this, guys? If it is a weak field ligand, less attraction, less attraction, it seems. Less attraction, less repulsion, and less rise in energy of Eg, and less splitting. Right, everyone? Do you know Hindi? हाँ जी, बिल्कुल, बहुत ही अच्छे से, एकदम अच्छे से पता है. क्या चाहते हो, अभी हिंदी में भी पढ़ाए? नहीं, इंग्लिश में पढ़ाएंगे. अच्छा, अब देखो, now that shouldn't have happened, everybody. Anyway, guys, so coming back to it, everyone. Now, what happened in crystal field theory was, remember we said that the anionic charge, I will come to it, Tanisha, don't worry. Pihu just explained, Bajra. If I try and explain it again, it will take me 10 more minutes and then we will be late, yeah? And then we'll be very late. Pihu, can you please watch it? Yeah, can you please just rewind and watch it again? Can you do that? Thank you. Acha. Okay, everybody, we were talking something else, right? Now remember that in CFT, we said that the ligands, the anionic ligands are point charges. Acha, if it is point charges, then it is supposed to be the strongest, no? It is supposed to be the strongest, isn't it? It is absolutely supposed to be the strongest, because if it is ionic bond, then hey, point charge, man, it's going to be super amazing. But that's not the case. How did we find out? Because we have something called a spectrochemical series. So Tanisha, here is your answer. Spectrochemical series bole to, spectrochemical series is something that is based on experimentation. Okay. Yes, it is based on experimentation, and we know that in spectrochemical series we have seen that, you know what, that I minus, Br minus, FCN minus, Cl minus, that means the anionic ligands are the weakest, bro. Yeah. So now do you understand the disadvantage of crystal field theory, everyone? Do you understand the disadvantage of crystal field theory? The assumption that we made killed it. This assumption that we made that ligands are point charges, metals are positive, this is an ionic bond, it's a purely electrostatic bond, they just killed it. That is why. Now, Tanisha, I am going to tell you another trick, everybody. Acha, in periodic table, P block elements, what are the first elements? What do you have? Boron, carbon, nitrogen, oxygen, fluorine, right? What do you have? You have B, C, N, O, F. Now remember it as fluorines are the weakest, as in the halogens are the weakest. Then if you have an oxygen donor site, that will be second weakest. Then if you have a nitrogen donor site, that will be third weakest. And carbon donor sites are usually the strongest, which is why carbon monoxide, CO, is the strongest field ligand that you have. Yep, makes sense? Again, hashtag EPBT, guys, in the chat box, everybody who has understood, hashtag EPBT, I need it right away, everyone. I need a little bit of motivation. Yes, so do we understand this? Everybody got the trick? What is the trick? Periodic table, P block element, what do you have? B, C, N, O, F. F is the weakest. Halogens are the weakest, then oxygen, then nitrogen, then carbon. carbons are the strongest. Clear hai? Chalo. All right. Now here you can see all of these, yeah? All these, the whole thing is written here. Yes, chalo. No worries, no worries. Okay. All right. Now there is something called as pairing energy. Something called as pairing energy. Chalo. Let's understand pairing energy with another story, everybody. So let's say that you all clear your IIT. Yeah, I mean you all clear your JEE mains, right? Yes. And once you have cleared your JEE, NO2 is weak or strong. Hey, ladki, you are not watching this thing or what? Can you not watch it? Tell me, no, where is NO2? Do you see NO2? And what did I just tell you? BCNOF. NO2 is an ambidentate ligand. If the oxygen side is the one that is donating, then it will be slightly weaker. If the nitrogen is the one that is donating, then it will be on the stronger side. So NO2 is actually somewhere here in the middle, it will lie. Somewhere here. If it is oxygen, then it will be here, ONO. If it is NO2, then it will be somewhere here. Okay? Pihu? Bacha, pay attention. Yes. Acha. Now, okay, coming back to your story, everybody. So let's say that you all have cleared your JEE mains and you have now reached the campus. Okay. Let's say that you all have reached the campus. Okay. Now in campuses, you know that you all have hostels, right? So in IIT Guwahati, I'm from IIT Guwahati. In IIT Guwahati, you had hostels like Brahmaputra, Siang, Subansiri, Dhansiri, Barak. These are all tributaries of Brahmaputra river. Do you guys know what is Brahmaputra river? Brahmaputra river is considered to be the only male river in whole of India, and it is one of the largest river of India, everybody. Yes. So all the tributaries of Brahmaputra river are the, are the hostel names. Okay. So now let's say that you go to the hostel. Yes. You go to the hostel and the hostel warden is there. The hostel warden says that, Bacha, there is a ground floor. There is a room in ground floor, but you will have to share it with someone. So what you ask? You are like, and which is the next room that is available empty? Now, the hostel warden says there is one room that is completely available. It's absolutely free. But it is in 4th floor. So you are like, okay, do you have lift? Hostel warden says no. Now which one will you choose? Which one will you choose? Which one are you going to choose? Are you going to choose the 4th floor? No lift. Every time you want to fill your bottle, come down. You want to buy a pen, come down. You want to eat some Maggi, come down. You want to buy a little bit of Coca-Cola, come down. You want to buy a book, come down. You want to go to the class, you have to come down and then climb up again. What are you going to do? You're going to choose an easy option out, right? And your easy option is to take the paired room in the ground floor. Yes. And exactly that's what happens with a ligand. When the splitting is a lot, the crystal field splitting is a lot, and there is a strong field ligand in play. The strong field ligand like carbon monoxide or Cn-, they're going to make sure that the splitting is so much that the electrons are like, hey, who will climb so much? Yeah? Let it be. They will pair up. At this point, what happens? The splitting is more than the pairing energy, hence they pair up. But if the splitting is less, then the pairing energy is more, then what they will do? They will be like, splitting is less, no. Now imagine if you have a next room, the next best room that is available is, let's say, in the 1st floor. 1st floor to ground floor, you can come down and, go easy, right? Right? Isn't it? If you just stay in 1st floor, then 1st floor too, you can easily go up and come down, right? That is exactly the story here. Now have a look, everybody. Now have a look. So what is happening? If you have a weak field ligand, it creates less crystal field splitting. Now delta octahedral splitting is lesser than pairing. So what will happen? You will get high spin complexes. What do you have? You will get high spin complexes. That means there will only be 1 electron in each orbital. Okay? Alright? But if the splitting is higher, pairing energy is less, then what will happen? You will get a low spin complex. That means in each orbital you might be having two electrons. Now everybody, can I have hashtag EPBT? Do we understand this pairing energy ka story, everyone? Yes. Acha, now, do you all see here what is written? Crystal field splitting energy here. See, minus 0.4 plus 0.6. The question comes in your mind. No, ma'am, what are these? 0.4 and 0.6. Remember that 2 by 5 and 3 by 5, everyone? Figure it out. If you do 2 by 5, how much do you get? And if you do 3 by 5, how much do you get, everybody? Calculate. 2 by 5 will give you 0.4. Yes? Now what is happening? 2 by 5 is at the bottom. 2 by 5 is at the bottom. So minus. And what is happening? 3 by 5 is going up like this. So that will be positive. Yes, that will be positive. NP. What is this N? N is the number of pairs of electrons available. What is N? N here is number of pairs of electrons. Clear hai bachos? Is everything? Yes, simplify. What is EPBT? EPBT is easy peasy biryani tasty, because ma'am, your NB ma'am loves biryani. So anything that has biryani, it has to be tasty. So we say easy peasy biryani tasty. Break headache. Ay, why break headache? Acha, now can we come to tetrahedral complex, bacha? This is done. Octahedral, have we understood clearly? Yes. Do we completely understand octahedral complexes, guys? So can we go to tetrahedral? EPBT? Great. Okay. Tetrahedral, same story, but tetrahedral, everybody, let's understand here what happens is, this time it's your some relative who bothers you. Okay. There is some relative who bothers you, and what happens is, you are the T2. The three siblings, they went up. The three siblings, they went up, and the parents are like, oh, this fellow is very good. Like imagine a Sharma ji ka beta who is very good in education. He is getting rank 1 in everywhere. Then what will happen? The moment those type of cousins and those relatives come, your parents are also going to bother you. Look at him, learn from him. Look at him, learn from him. So what happened? Your anger will go up, and your parents will be like, oh, very nice. My daughter and my son will learn something from them now. So their energy will come down. So what happens is, but see everybody, did I not tell you that in tetrahedral complexes, because of no symmetry, gerad means symmetry, because we do not have symmetry here, hence we are going to not write G here. See, we are only writing E and T2. What are we writing? We are writing only E and T2. Clear? Chal. Okay, now let's have a look at this, everybody. Okay, break. Seriously, just 1 hour, guys. 1.5 hours only. I started at 9 o'clock. From 9 o'clock to 10:30, you need a break. Hut. Study. Study. No break. It's going to be only 2.5 hours or so. Oh, very good, Raghu. All the very best. Chalo, guys. Hybridization of NiCO4. Okay, coordination number here is 4. As we can see, there are 4 ligands that are attached to nickel. Now, does everybody know what are the 3D series atomic number? Do you all know? Do you all know 3D series atomic number, everybody? What do you have? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, right? What is it? Sachin Tendulkar, very crazy man, free coaching, Nick's cousin. Write it down. Write it down right now. This is how you remember. D block, first series that you have. D block elements, first series that you have. Yes, Scandium, Sachin Tendulkar. Yes, Tendulkar, titanium, vanadium, very, Cr, chromium, crazy, Mn, manganese, man, free, Fe, coaching, cobalt, Nick, Ni, cousin, Cuzn, cousin. Okay, you know. Hey Ragul, right now if I do it, bacha, this class will get this thing. Do you mind watching the structure of atoms session that I have already made. Yes, I have already made a structure of atom session. Please go watch it, okay? Yes. Yeah. Okay. So, nickel. What is atomic number of nickel? Nickel is, what did I just tell you guys? Scandium, titanium, vanadium, chromium, manganese, iron, nickel. Iron, cobalt, nickel. Nickel is 28, isn't it? Nickel is 28, everybody. Okay? Yes? Pihu, we haven't learned that because that has Hindi, right? This is an English channel, so we only talk in English here. Anyway, so nickel has an atomic number of 28. So 28 means 3D8, 4s2. Now we all know that CO is a strong fill ligand, right? So what will happen here is, check it out, 3D8, isn't it? 3D8. So how do I write it? 1, 2, 3, 4, 5, 6, 7 and 8, right? 8 electrons, I have filled it. 4s, here I have 2 electrons, right? Now I know that CO is a strong fill ligand, but what is the oxidation number of nickel? Now CO is also neutral, by the way. CO is a neutral ligand, okay? So that means 4 into 0, that means nickel is in 0 oxidation state. None of the electrons are going, anywhere. Now what happens, but CO, yes, carbon monoxide, CO right here needs 4 rooms. 4 CO are going to come, right? So they need 4 rooms. Now what will happen is, this s orbital, right? This s orbital here, sp3 hybrid orbital, 4 pairs of electrons from 4 CO, outer orbital complex will be formed. Yes, these s orbitals, they will be pushed here and sp3 will be made empty. CO will come and fill the sp3 orbitals, and that is how we are going to get the compound. Okay, that is how we are going to get the complex, everybody. Now are you getting it? Pihu, see examples, everybody. I'm giving you examples. Now for CONH36, similarly you have to do this, where I think that by now you already know how to calculate, how to draw these diagrams and how to find the magnetism, everybody. Please know that you don't have to remember exact exact value of Bohr magneton. Always do one thing, that is, how much ever number of unpaired electrons are there, your Bohr magneton will be almost similar. For example, if you have one unpaired electron, the magnetic moment will be equal to 1 point something. If it is 2, then it will be 2 point something. If it is 3, then it will be 3 point something. If it is 4, it will be 4 point something. So do we understand all of these, everybody? Yes, do we understand? Great. Chalo. Now everybody, let's say the hybridization involved in this complex. See, this is a JEE Main 2015 question, everybody. Yes, what is this? JEE Main 2015 question, everybody. Have a look. NiCN4 2 minus. Okay, that's your compound. Now we have to find out the hybridization. Okay, so first of all, what do we have to do? We have to calculate the oxidation number. Here X, Ni is equal to X, plus we know that Cn is a negative, it's an anionic ligand. So 4 minus 1. Are Baba, I will tell you isomerism we haven't reached. Yeah, we haven't reached isomerism, Tarun. Am I going? Did I say that the class is over? No, wait, chill. I'll tell you. So x plus 4 into minus 1 is equal to minus 2. That means x is equal to plus 2, right? If it is plus 2, that means nickel is in plus 2 oxidation state. That means it will have 3D8. If it is 3D8, that means I can write it as, okay, I guess you are not able to see it. So 1, 2, 3, 4 and 5, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? Now we know that Cn is a strong fill ligand. This pairing will happen. Yes, this pairing will happen, and it has S and P3, right? 1, 2, 3. So what will happen now? What will happen? It will take up 1D from here, D it will take, S it will take, and P2 it will take. So it will form DsP2 hybridization. Hence option D is the correct answer. Yes? Yes, no, B and C are not same. One is D2sp2, one is D2sp3. Done, guys. Yes, chalo. Next question, everybody. Let's make it fast. Now this is JEE Main 2012 question. you are asked a low spin complex of D6 cation in an octahedral field will have the following energy. And delta O is crystal field splitting energy in an octahedral field, and P is equal to electron pair energy. Remember, I have just given you a formula, everybody. I have just given you a formula, guys. Yes, what is the formula that I gave you? What is the formula that I gave you, everybody? I've just given you a formula, guys. Do you all know? I've just given you a formula. Yes, what was it? Remember, minus 2 by 5 x, let's say, plus 3 by 5 y, yes, this is delta O, plus n p. That's the formula, right? Now you are saying D6, if it is D6 and low spin, everybody. If it is low spin D6, that means T2G will have 6 electrons. All the 6 electrons will be in T2G. That means if this X right here and Eg will be equal to 0, right? There will be no electrons in Eg. There will be 6 electrons in T2G. So this, if I calculate, and number of paired electrons, there are 3 paired electrons, right? There are 3 number of paired electrons, couples, right? So what will I get here? 2 by 5 minus 2 by 5 multiplied with 6, and here you will have 3p. So minus 12 by 5 plus 3p, that means option B is the correct answer. Make it sense with everybody? Please have a look and tell me, does it make sense? That's it. Yes, have a look, everybody. This is clear? This is clear, right? Yeah? Yes, option B is the correct answer. Chalo, great. Next question, everyone. The difference in the number of unpaired electrons of a metal ion in its high spin and low spin octahedral complex is 2. Which metal ion is it? Okay. Our first option is Ni. Okay. Our first option is Ni. So how do we calculate this? Okay. For Ni, let's calculate. Now, Ni, we know that the atomic number is what? 28, right? If it is 28, that means we have 3d8, 4s2. But Ni is in plus 2, that means this will go away. So, we will have 3d8, correct? If it is 3d8, everybody, then for a low spin complex, how do we draw it? We will have 1, 2, and 3. And we will have Eg 1, 2, right? Low spin. So 1, 2, 3, 4, 5, 6, 7. And 7 and 8, right? 7 and 8, let's say. Yeah. So this is your low spin. Correct? Now for high spin, everybody. High spin, what will we have for high spin? For high spin, let's say 1, 2, 3. And 1, 2 here, right? For high spin, we will have 1, 2, 3, 4, 5, 6, 7. Correct? Is it going to be this? 6, 7, and 8. Oh, sorry. Going to be like this. Now it's correct. So now, here, number of unpaired electrons are 3d8, no? 3d8, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes. This is the correct answer. Number of unpaired electron here is 2 and here it's 0. So 2 minus 0 is 2, right? Option A. I think it's option A. Everybody have a look. Please read the question and understand. Value of X and Y. I told you, na Baba. Y is number of electrons present in Eg. X is number of electrons present in T2G. That's how we calculate it. Okay. That's how you calculate it. Yes, Ammo. It will be good for you also. Yes. It will be good for you also. Abhi, I will start DNF block as soon as this is over, guys. Yes, do we understand this? Okay, next. Among the following species, the one which causes the highest crystal field splitting delta O as a ligand is, everybody, can you tell me this? Very simple, very easy. The moment you look at it, you have to understand that CO is the strongest ligand. Hence, this is the one that is going to give you a highest crystal field splitting energy. Great. Okay. Now everybody, let's talk a little bit about the magnetic properties of the coordination compound. Okay, what about magnetic properties? We know that magnetic properties is very closely related to the number of unpaired electrons, right? Yes, the more number of unpaired electrons are there, the magnetic moment is going to be more. Less number of unpaired electrons are there, magnetic moment is going to be lesser, right? How do we calculate it? This is the formula. Mu is equal to n multiplied with n plus 2 root over, and the unit is Bm, that is Bohr magneton. What is the unit? The unit is Bohr magneton. Okay, yes, everybody clear? I'm not gonna go too much into it. This all you know. Now let's talk about color of coordination compound. You know, coordination compounds are famous for showing colors. Yes, why is it that they can show colors? Now, number one is that they go for DD transition. What is DD transition? Did you all see? Everybody have a look, guys, have a look. Remember the crystal field splitting, everybody? Here what happened is, let's say that if I have an electron here, yes, the moment it gets a little bit of energy, it is going to jump and go here. Now both T2G and the EG orbitals belong to the D orbitals. And because the electrons are transitioning from T2G to EG, both of them belonging to D orbital, we say that this is a DD transition. Okay, this is a DD transition. The formula is, you will get PDF, bacha. You will get PDF in the Telegram channel. You will get PDF. Srinidhi, we will be discussing PYQ in the PYQ session. Okay? Yes, we will be discussing it in PYQ session. Please check last question you have done wrong. No, Pratha. No, Pratha. Is it CO plus 3? CO plus 2. Oh ho ho. Is it CO plus 2? Oh my God. Yes. Thank you so much. Who is it? Yes. Okay. So, a huge blunder has happened, everybody. Huge blunder. Thank you so much. Here. First of all, you have to understand that, okay, everybody understand this, that this high spin and low spin, right, it is not applicable for nickel at all, because D8 is not possible. We only do it for D4 to D7. Yes, we only do it for D4 to D7 and not for D8. Yes, very good. Thank you so much, Piyu. Thank you so much. Yes, my mistake. For CO, let's have a look, everybody. CO will have what? 27 atomic number, right? 27 means 3D7 4S2. So CO in plus 2 state will have 3D7. Now for low spin, we will have T2G here and EG here, right? So 3D7, so 1, 2, 3, 4, 5, 6 and 7, right? Yes. If it is high spin, then what we have? If we have high spin, then we have EG here and we have T2G here, 1, 2. So we will have 1, 2, 3, 4, 5, 6 and 7. Now it is correct? Yes. So here number of unpaired electron is 3 and here number of unpaired electron is 1. So 3 minus 1 is 2. Yes, option C is the correct answer. Very good. Yes. Thank you, Vaishnavi, for teaching me English also. Thank you so much. Hey, Warner's theory, please read it from NCERT book, bacha. Please understand, no? Cut me some slack. Understand that 2 big chapters I'm taking, right? 2 big chapters I'm taking right now. And you want me to get into the detail. Tell me something. Can I take a session for 18 hours? No, bacha. So please understand that, Harsha. I think Warner's theory, you can read it on your own. I'm completing all the other things, right? Yes? Got it? Yes, this question was very easy. Okay, now we are done with it, everybody. Somebody had asked me how to calculate magnetic moment. Okay. Chalo, let me show you here, huh? Let me show you this here, everybody. See. Yeah, Warner is very easy. Yes, Manjushri, telling you. See, the formula is mu is equal to root over n multiplied with n plus 2. N is the number of unpaired electron. Got it? For example, let's take Mn, or no, let's take Fe plus 2. Okay? Let's take Fe plus 2. What is the atomic number of iron? Scandium, titanium, vanadium, chromium, manganese, iron. 26. So 26 means it will have 3d6, 4s2. Now I'm saying that plus 2. That means 2 electrons are gone. If 2 electrons are gone, that means it will have only 3d6. If it is 3d6, that means there are 4 unpaired electrons. Now just put it in the value. You will get 4. 4 plus 2 root over, that means 4 plus 2 is 6. 6 4s are 24. Root over 24 will give you what? Root over 24 will give you 4.8 or 4.74, something like that. This is what you will get, and that is your correct answer. Okay? This is how you calculate. This is how you calculate. Got it? Yes? Let's hope so. If it doesn't end, then doesn't end. We will continue for longer. What else? Okay. So yeah, DD transition, everybody, did you all understand what is DD transition, guys? DD transition, I was telling you. I hope that you understood what is DD transition. These all, whatever is written here, you can just read it, and that tells you that what is DD transition. By the way, one thing that is important in DD transition here is, everybody, there is something called as a color wheel, right? There is something called as a color wheel. What is this color wheel, everybody? You all know? Yes, so all you have to do is do this, and here. Now you all know VBGR, right? Don't write I. Just start from here. V, B, G, Y, O, R. You know that whatever is absorbed, complementary color will be shown. So if you have something in violet color, that means yellow color has been absorbed and you are getting violet color. Yes? All right, everybody. Yes, Somesh Rao, what is your doubt? Write down. Instead of writing, I have a doubt, that way you waste more time, because I have to ask you what is your doubt, then you will write your doubt, then I have to answer. Just write the question, okay? Yes? Chalo. Cool. So this is one important thing in color of coordination compound. Now, stability of coordination compound. Acha, stability of coordination compound, this was given by somebody called as Sidgwick. This name always reminds me of Harry Potter book. I don't know why. So instead of going through all of these, let me, where is an empty page? We do not have an empty page here. We're supposed to have an empty page, right? 1 second, guys, 1 second. I need to write down something, but I'm not finding empty pages here. Okay. Just a second, people, just a second. What did I do? Yeah, I'm trying to. That's not happening. Done. Okay, here we go. Yes. So there is something called as effective atomic number, which tells you about the stability of coordination compound. Okay, what is it? Effective atomic number. effective atomic number. Yes, it tells us about the stability of coordination number. Stability of coordination. Golden guys, how will you start? When will you start? Bacha, can you not see I am teaching you? I am teaching you, right? Have you seen me not talking, just standing here, dancing around? No, right? Can you please wait? Let me finish one chapter only, then I can go to the next chapter, right? How do you want me to go to DNF block just like that without completing this chapter? From that time, you're going on asking, when will you start this? When will you start this? Can you not see I'm taking a session? I'm continuing teaching you, right? Please stop doing that. Understand that I am teaching you any which ways. Okay. Now this is very simple, very easy. Okay. This effective atomic number is very simple, very easy. Sedgwick said that, yes, Sedgwick said that, for example, let's take 𝐸𝐶N6, yes, 𝐸CN6, the whole class I have taken only one example, 𝐸CN6, right? And remember it had K4, so let's say that it has 4 minus, okay, 4 minus. In this case, if you calculate, you will see that Fe is in +2 oxidation state, okay? Alright, so that means 26, right? 26, correct? From 26 minus 2, that means how much is the how many number of electrons will be there? 24 now, right? 24 altogether, plus what do you have here? 6, right? So you take here 6, and then what you do is number of electrons that are donated by the ligand. So 6 ligands are here, all the 6 of them are going to donate 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, right? Correct, everybody? So that means 6 multiplied with 2. Calculate this. What will you be getting? What will you be getting? You will be getting 6 into 2 is 12. 12 plus 24 is 36. And 36 is what? It's 36 is a noble gas electronic configuration, right? Yes. 36 is a noble gas electronic configuration. So yes, this means that this is going to be stable. This is going to be stable. But if you have any other element which does not look like it's a noble gas electronic configuration, it's not going to be stable. Understood? This is simple and easy, everybody. Is this simple and easy? Great. Chalo. All right. All of these theory that is written here, that you can study it later. Okay, all of these you can study. Chalo. Now let's start with isomerism. Again, isomerism is something that we have studied in organic chemistry as well, but here also we will have to study. Okay, so before isomerism, one last thing, everybody. Before isomerism, there is one last thing that we have to understand, and that is yes, metal carbonyl. We haven't yes, Kundan, what happened? What's your doubt? What's question? What is your question? Yes, tell me. Now, while we are studying metal carbonyl, let's also understand something that is called as synergic bonding or back bonding. How many of you know that? I'm pretty sure you know it, but it's my duty to teach you. So back bonding, or it is called as synergic bonding, everybody. Yes, what is it? Synergic bonding or back bonding, we call it. Now, everybody, let's understand this. Let's say especially for metal carbonyl, or you have other examples. Okay, examples, you know which ligands can do it? CO, yes, then you have Cn minus, then you have NO plus, right? These kind of ligands, okay, these kind of ligands, you know what happens? They can go for back bonding or synergic bonding. So what really happens is, for example, let's take CO, right? Now CO, everybody, do you understand that CO, let's say, right? Yes. And here, let's say that I have the metal. So we understand that here, right here, there will be a sigma bond that will happen here. A sigma bond that will form. But you also understand that right here, this will have certain, remember molecular orbital theory, everybody? Do you remember, everyone, molecular orbital theory? In molecular orbital theory, do you remember there were bonding and anti-bonding orbitals, right? Yes? Do you remember that there are anti-bonding and bonding molecular orbitals? So this metal now says that, acha, you have formed sigma bond, great. If you have formed sigma bond, that means that you also have empty anti-bonding p orbital, right? So what the metal does is, now the metal gives it back again and forms a pi bonding. Did you see what happened, everybody? Did you see what happened? Yes? So the ligand had electrons and the ligand gave it to the metal, it formed a sigma bond. Now the metal has the electrons and the metal says that, hey, ligand, you have anti-bonding empty orbitals. So the metal gives back the electrons and it forms a pi bond. Now everybody try and understand it this way, that right here what happens is, this ligand has accepted a pi bonding, right? So this ligand, my dear student, can I call this ligand? This ligand is a pi acceptor, right? Because it just formed a pi bond with the metal because of back bonding. Correct, everyone? Correct, everybody? So this ligand is a pi acceptor, right? Great. Somebody who accepts, what do we call them? Somebody who accepts electrons, what do we call them? Lewis acid? Don't we call them Lewis acid? Yes, Lewis acid. So what can I call it? I can also call it as pi acid ligand. Yes, pi Lewis acid ligand. Can I call them that? Absolutely. So this is the whole concept of this metal carbonyl pi acceptor, synergic bond, back bonding, everything, right? Do you all understand all of these? Yes? Do you all understand all of this? Great. Now, let's quickly go to isomerism, everybody, okay? Let's quickly go to isomerism. Now, there are different types of isomerism. Broadly, you can classify them as structural isomerism and stereoisomerism. In structural isomerism, you have ionization isomerism, you have hydration isomerism, you have coordination isomerism, linkage, ligand and coordination position. Okay. All right, everybody. So, chalo, let's have a look at it. And stereoisomerism also, let's have a look at the definitions basically. Now, in ionization isomerism, my dear students, please look at the examples, everybody. What happens is you have CONH3 5SO4 and NO3 is outside. Similarly, now you have CONH3 5, NO3 is inside the coordination entity, SO4 is kicked outside. So do you understand what is ionization isomerism? In case of ionization isomerism, the counter ion in a complex salt is a potential ligand. The counter ion is a potential ligand. Getting it? Okay. Now, let's go to hydration isomerism, guys. Hydration isomerism, what happens is there are different number of water molecule in the coordination entity. For example, you have CONH3 4H2O, Cl2 here, and here you have CONH3 4Cl2 Cl.H2O. See, no water molecule inside the coordination entity. Understanding, everybody? Understanding, guys? Great. Now, let's go to coordination isomerism. Coordination isomerism, when it arises, when you have, see, CuNH3 4 PtCl4. You have two coordination entities, right? In a complex. In a complex, you have two coordination entity. Now, see. Now, what we are doing is Pt, we are putting it with NH3 4 and Cu goes with Cl4. So Pt NH3 4 Cu Cl4. When you exchange the coordination entities like this, then it forms a coordination ligand. Okay. All right. Then it forms coordination ligand. All right. Yes. No catalyst or solution needed in ionization. Ionization. No, nothing as such. Just understand this. It's fine. Just understand these. It's fine. Then we come to linkage isomerism. No, basically what I'm saying is in ionization isomerism, right? There are two different coordination entities. There are two different coordination entities which can act like ionization isomerism. Okay. Shravanand, can you please do me a favor? Just rewind it and watch it, because if I continue again, I'll be taking more time. Okay. Yeah. Please do that. Okay. Chalo. Next, everybody, what is linkage isomerism? Linkage isomerism arises when you have an ambidentate ligand, right? Because it can hold on to the metal like this way, or it can hold on to the metal with the left hand. So that's when you have ambidentate ligand. Then you have ligand isomerism, coordination compound which have same stoichiometric composition and same molecular formula, but the connectivities with the ligands are different. For example, have a look. You have CO, TN2, it should not be TN2, guys. I think, okay, yes. When you have 1,3-diaminopropane, this we are writing as TN. And when we have 1,2-diaminopropane, we are writing this as TN. Do you see what is the difference, everybody? Do you see what is the difference? See, basically like positional isomers that you have read, remember? Position isomers in organic chemistry. Haven't we studied that? Exactly. So similarly like that, see here the position is 1 and 3, here the position is 1 and 2. Okay, that's called as your ligand isomerism. Alright. Then you have coordination position. So guys, I think I'm going to cut it a little short, everyone. You can go through all of these things, yeah. And here is a cheat sheet for you all, that what is the compound formula, what is the coordination number, and how many number of geometrical isomers are possible. This is in case of stereoisomerism. Okay. Shravanand Bacha, I just told you that. Okay. For example, where is it? So you have carbon and oxygen, right? Now, this carbon has electrons that it can donate to the metal. When it donates to the metal, it forms a sigma bond, right? It forms a sigma bond, correct? After taking the sigma bond, now this carbon, in case of molecular orbital theory, have you studied molecular orbital theory in chemical bonding chapter? In molecular orbital theory, you have bonding orbital theory, anti-bonding orbital theory. Remember pi star? There's something called as pi star, sigma star. Do you remember? Do you remember? Yes. So now this metal, once it has taken the sigma, once it has taken those electrons, it takes it and then sees that, oh, you still have an empty anti-bonding pi orbital. So it gives the electron back and forms a pi bond. Understood? That's what I've told you. Okay? That's what I've told you. Okay? Chalo guys, moving on. Let's finish this chapter quickly. Acha, now let's do this, everybody. Let's do this. Let's do this. Okay? Quickly. Manjushri, IUPAC name of the ionization isomerism. Bacha, I think I've taught you how to write IUPAC name. You tell me, no? How will you write it? How will you write it? You know the whole rule, right? What is cis and trans? Okay. Chalo, let me draw cis and trans. I'm going to explain this to you right now. Chalo, draw the geometrical isomerism of, let's say that you have PTCl, what? PTCl2NH3PY, pyridine, right? Okay. So what do you have? You have, okay. Have a look, everybody. Have a look. Yes, bond length is less in back bonding. Yes, the bond length reduces in back bonding because there are two bonds, right? We know. Bond order increases, bond length will decrease. Yes, Pihu, absolutely. Guys. Harsha, please yaar, padh lena, geometrical and optical isomerism. You all know, na? You all know. Don't pressurize. Everybody, you are like sitting on my head now. Ma'am, do this also. Ma'am, do oneness theory. Ma'am, do DNF block. Please. Okay, please. See, now she wants stereoisomerism. Explain. But just stereoisomerism, there are two types of stereoisomerism: geometrical isomerism and optical isomerism. Optical isomerism are those that can rotate the plane polarized right. If it rotates it into right side, dextro. If it rotates to the left side, levo. Geometrical isomerisms are cis, trans, facial, meridional. Okay, all right. So you have FEC-MER. What is FEC-MER? When you have, let's say, when you have, let's say, M and you have A, let's say A, and you have B, B, B. If you have something like this, then this will be facial. And if you have, let's say, 1, 2, 3, 4, 5, 6, if you have A, B, B, A, B. If you have something like this, then this is going to be meridional. Okay, this is meridional, this is facial. Cool? All right? Yes. This is what you get. In optical, you have dextro and levo. Chalo. Now everybody, let's do a question and we understand what is cis and trans. Okay? Let's understand cis and trans, everybody. So, let's draw the structure. So, you have PT. PT is your central metal atom. Now, you have Cl2, 2 Cl. So, 1 Cl here. Let's say 1 Cl here. Now, what am I going to do? I'm going to write NH3 here and I'm going to write pyridine here. Now, who asked me? Who was it? Who was it? Oh, thank you, Shravan, thank you so much. Who was it? Somebody had asked me, ma'am, what is cis and trans? What is cis and trans? Who had asked me? What is cis and trans? Tanisha. Tanisha, have a look, bacha. See, Cl and Cl, both are on the same side, right? If both are on the same side, we call this to be a cis isomer. Now, if I draw the same structure as this, Cl, Cl, NH3 and Py. Now, do you see the Cl and the Cl are on the opposite side? If it is on the opposite side, then we call it as trans. So, how to remember it? Same side, same, cis. Trans. Trans is transportation. Transportation happens on road. On the road, you have two-way traffic. So, opposite sides, trans. That's how I remembered it. So, if you want, you can. Acha, now the next question, everybody see. Cr. Gly. Gly is what? Gly, I told you. Gly is a glycine. Glycine is a bidentate ligand. Okay. Glycine is bidentate. Okay. What is it? Bidentate ligand. Cool you? Yes. So now have a look, everybody. Have a look. Now you must be thinking that ma'am, all the three ligands are same. How come this will have cis and trans? It should not be showing this geometrical isomer. No. Here is a twist, everybody. You know how to draw glycine. Glycine is a bidentate ligand. I've just told you, right? That means glycine looks like this, guys. You have NH2 here. You have OH here. And here you have double bond O. So that means that this N can be the donator. This O can be the donator. Now that there are two donor sides, tell me, can you have a geometrical isomer? Yes, you can. Yes, you can. See, what you can do is, here, let me draw it with another color. So you have Cr here. Let's say that 1, 2, 3, 4, 5, 6. Cr, 1, 2, 3, 4, 5, 6, right? So have a look, everybody. What I can do is, I can do gly here. Now, see, what did I tell you? N and O. N and O, there are two donor sides, guys. So I can write it as, this can be my oxygen donor side, this can be my nitrogen donor side, this can be my nitrogen donor side, this can be my oxygen donor side, and once again, this can be my nitrogen donor side, this can be my oxygen donor side. I'm connecting. Similarly, everybody, have a look. Here I can write it as glycine, O-N, yes. Now, glycine, N-O, and I can write it as glycine, N this side, O this side. What happened now? This will be my trans, this will be my cis. That's it. That's it. Cannot see. Chalo, I'll move out. Have a look and understand. Oh, I think I also have a diagram of it. Can you see this? Can you see this? Tell me, is it all easy peasy biryani tasty? Done. Okay. Understood? Chalo, next question everyone. Okay. Which of the following complex species is not expected to exhibit optical isomerism? Anyone? Anybody? Oh, very simple, very easy. I have just showed you, right? Geometrical isomerism, facial meridional. See, this one will not be able to show optical isomerism, but it will show geometrical isomerism of facial meridional type. FEC-MER. Throw it and then beat it. FEC-ke-maro. Yes? FEC-ke-maro. Okay? So due to the presence of plane of symmetry, this will show you geometrical isomerism. It will not show you optical isomerism. Cool hai? Moving on. Acha, read this question carefully. This is JEE Main 2014 question, everybody. Read this question, guys. Yes? Read this question. An octahedral complex with molecular composition M.5 NH3, sorry, not M5 NH3 ClSO4 has two isomers, A and B. Now, the solution of A gives white precipitate with AgNO3 solution, and the solution of B gives white precipitate with BaCl2 solution. The type of isomerism exhibited by the complex is anybody guys? Anybody? This has got to be ionization isomerism, isn't it? Because the counter ion is a potential ligand. So when the counter ion is different, it is dissociating and it is giving you different tests. Yes, it is ionization isomerism. See, the question is so big that you read it and you feel like, oh my god, this is very confusing, but it's not. It was so simple, so easy. Chalo, next question. Which one of the following complexes is not expected to exhibit isomerism at all? Anybody? Which one? Okay. So, listen to me, everybody. Compounds that have a tetrahedral geometry. Yes, the compound that have a tetrahedral geometry will not exhibit isomerism here. Why? Because of presence of symmetry. Because of presence of symmetry. So which one is it? Option D. This will not show you. This will not give you isomerism because of presence of symmetry. Okay? Yes. Tetrahedral. Very good. So these are chemistry classes. Very good. Chalo guys, now we come to DNF block. All the students who have been asking me for DNF block. Alright, chalo guys, come back, everybody, come back, let's have a look at it. So your D and F block, my dear student, this is where you have the D block and this is where you have the F block. The F block have been already pushed out of the periodic table. Nobody cares about them, even we don't care about them so much. Because and the chapter is also very small. It is going to be it is going to be very small. So we're going to brush it up basically. Okay, so now in D block you have this is called as this scandium to zinc. This is called as your 3D series. You have here, everybody, yttrium to cadmium. This is called as 4D series. Then you have lanthanum to mercury. This is called as 5D series. And the last one, that is actinium to copernicium. This is called as your 6D series, everybody. Okay, this is called as 6D series. So these are the 4 series that you have. Now you are ideally supposed to learn the atomic number. However, if you just know the first series, then you can calculate it, everybody. You can always calculate it. For example, the first series, like I told you, scandium. Everybody start counting from here. Scandium has a 21 atomic number. Titanium has 22. Vanadium has 23. Chromium has 24. Manganese has 25. Iron has 26. Cobalt has 27. Nickel has 28. Copper has 29. And zinc has 30. Alright, now here you have certain exceptions, everybody. Shall we talk about the exceptions, everybody? Are you all with me? Chalo. Your exceptions are copper. Yes. Your exception is, next exception here is chromium. Yes. Then you have Ag, Au, Okay. Then you have platinum here. Okay. Then chromium is done. Then what do you have? What was it? Copper, silver, gold, platinum, corrupting, new bureaucrats, niobium, new bureaucrats, money taking, rupee rhyming, pandis. Yeah, this is how I learned, everybody. Yeah, guys, did you hear me? So these are your exceptions. Okay, this is where you will write the exceptional electronic configuration. How do you remember it? Your exception is, say it with me, everyone: copper, silver, gold, platinum, corrupt, new bureaucrats. New bureaucrats. Bureaucrats, you know who are bureaucrats? Bureaucrats are these IS, IPS officers. They are called as bureaucrats. Okay. So new bureaucrats, it corrupts, as in copper, silver, gold, platinum corrupts the new bureaucrats. Money taking, rupee rhyming, pandi. Pandi means pandi means pig in, I think, Kurgi language. I'm not sure. Pandi means yeah, pandi means pig. Okay. So yes, so these are your exceptions. Now, if somebody asks you to write their electronic configuration, let's have a look at it, everybody. सबसे पहले, first of all, PD has a different electronic configuration than everybody else, that is palladium. Palladium has an electronic configuration of, my dear students, it has 5D0, 5D0 it seems, 5S0, 4D10, okay, that is palladium's electronic configuration. All right, yes. And all the other ones, if you ask me, for example, chromium has an electronic configuration of, everybody, you know that, right? 4s1 3d5. See, this is different because we write all the other electronic configuration as 4s2 3d1, 4s2 3d2, 4s2 3d3, 4s2 3d4, right? But you all here, these are the ones that will have exceptional ones. So here you will always have 5s1. What will you have? 5s1. Okay. For example, AG will have, again, AG will have 5s1 4d10. Similarly, copper will have 4s1, 4s1 3d10, right? So you get the point. You get the point. Now will you all be able to write it? What do you have? Copper, silver, gold, platinum, corrupt new bureaucrats, money taking, rupee rhyming, pandi. Okay. This is my mnemonic. I don't think you will be finding it anywhere else. You will not find it anywhere else. This is not on internet, guys. This is my this is my mnemonic, everybody. Okay. Now coming to the next point that we all know, and this is that zinc, cadmium and mercury, they are not transitional elements. They are definitely D block elements, which is why we study them, but they are not transition elements. Everybody knows the definition, and they all know that why, because if an element is transition element, then they are supposed to have half-filled d orbitals in their elemental form or in their simple ions. Okay, in their simple ions. All right, this is the definition. Hence we know that zinc, cadmium and mercury, they are not transition elements. Okay. All right, everybody. All right. So we have understood this. Great. Now the properties of D block elements, you all have to understand that because they are all metals. In this particular block, we see that almost all of them are metal. I found out in Google exactly same one. What are you saying? You're lying, bro. You are lying. This cannot be on Google because I did not type it out in Google, yeah? This is mine one. I made it. Now you see. Now you're calling me a liar. This is not right. Not right. Not right. Chalo. So because these are metals, you have to understand that most of the properties that metals exhibit, they are going to show the same properties, right? For example, they have high tensile strength, they are very ductile, they are malleable, you can beat them into sheet, and all of these things are obviously there. They have high thermal and electrical conductivity, metallic luster, they are very hard, low volatility, etc., etc. All of these that are there, okay? Now, in case of properties of D block, we have to understand another thing, and that is the formation of colored ions, which we have just studied in coordination compound, and that was because of DD transition. But DD transition is not the only thing why they show color. There is another reason why they show color, and that is called as charge transfer spectra, everybody. And what is this charge transfer spectra? Let's have a look at it, everyone. Remember, for manganese, yes, manganese, everybody, you all know that manganese can go to +7 oxidation state, right? So in MnO4 minus, manganese goes to +7 oxidation state, and yet potassium permanganate has what? Potassium permanganate has a purple color. So DD transition cannot happen. I mean, come on, Mn+7, it has no D electron at all. How can it be DD transition? It cannot. But oxygen has that negative charge. That negative charge can be transferred to manganese, and that is why it shows the color of purple, which is why this is called as charge transfer spectra, everybody. Clear hai? Is this clear? Is this clear? Is this clear? Similarly, vanadium. Vanadium, when it goes to +5 oxidation state, it can still show color. Yet it does not have any d orbital, guys. Yes, are you understanding? Now, d block elements, they are most popularly known for their various oxidation state. Yes, they have various oxidation state. What is going on in the chat box, guys? How am I a robot? Mark how pitti. Virtual punch. Shreyas sir told, no, virtual slap and all you will get. You will actually, that will happen anyway. So the most popular thing that we know about is that they can show you variety of oxidation state. You know why? Okay, so you remember that when we talk about oxidation state, I kept telling you that there is a trick, right? There is a trick, everybody. Group 1 +1, group 2 +2, group 13 +3, group 14 +4 or -4, group 15 3 2 1 again, right? These were the group oxidation state, but here we cannot say that. Why? Because they have, everybody, these particular elements, right? These particular D block elements, they have something that is very, very nice, and that is that the energy levels, the energy gap between the ultimate shell, that is the last shell, and the penultimate shell, it's so close. The energy level is so close that, so understand this, okay? Let's say that Gangula and Nagasai, okay? Let's say that I have two students in my class, Rajashekhar and Nagasai. Now Rajashekhar in one of the tests gets, let's say, 39 point, okay? Let's say Rajashekhar in this test is getting 39.7 and Nagasai got 39.8. The mark difference is very less, right? Very less. Now, Rajashekhar cannot chill. Rajashekhar cannot think that, oh, next time I'll be able to do better. Or Naga also cannot think that next time I will be only the topper. It's so less that both of them will have to be on their toes. That no, next time I have to do better. Next time I have to do better. Next time I have to do better. Because the energy level is so close that the moment Rajashekhar takes it a little chill, Naga will be the topper. The moment Naga takes it a little chill, Rajashekhar will be the topper. You get my point? Exactly, this is what happens. The ultimate shell and the penultimate shell, the energy levels are so close that not only the last shell participates, but also the penultimate shell also wants to participate in chemical reaction, and they also want to give away their electrons, which is why everybody remember it that, okay, so you have 1 2 scandium is third group, right? Third, scandium, titanium, vanadium, chromium, manganese. Please remember it that group 7 has the highest oxidation state always, okay? Who has? Group 7 has highest oxidation state, just like manganese, right? You see manganese has highest oxidation state. Yes, and in the whole D block, it is Ru and Os. Ru and osmium, Os, they have +8 oxidation state, which is the highest oxidation state everywhere, okay? All right, now the most common oxidation state that you see in this D block elements is +2. +2 is the most common oxidation state, except scandium. Scandium has what? 3D1 4s2. Once it gives away 3 electrons, it is super chill because it has attained noble gas configuration and now it does not want to participate anymore. Okay. All right. Everybody else, out of 40 guys. Yes, Karthik and Naga, out of 40 you were getting 39.7 and 39.8. So chill. Okay. And I think that's it that I had to tell you about oxidation state. And what else? Acha, chalo, let's keep going. Yeah. Catalytic property. Yes. So color is done. Magnetism, we will read about it. Oxidation state is done. Acha. Oh, one more thing, everybody. Color, right? Now color depends on certain properties, everybody. We have just read it in coordination compound, right? Nature of ligands. What is the nature of ligand? If it is weak field ligand, color will be property. If it is strong field ligand, very good color you get to see. Geometry of the complex, if it is octahedral or tetrahedral, obviously, because then also the splitting differs, right? So geometry of the complex will also be a factor while deciding the color. Finally, presence of unpaired electrons obviously will be a deciding factor of color, right? So I think we have understood all of this, right? Now we go to properties of d block element, catalytic property. So first of all, why do these guys, why do they show you catalytic property? Any idea? Have you thought about it, that why do they show you catalytic property? First of all, you have to understand that they can show catalytic property because they have a large surface area, because these guys are bigger, right? They have larger size of atoms as well. So yes, they have larger surface area, right? They have variable oxidation state. We have just spoken about it, right? They have what they have? +6, +7, +5, +3. They can show so many oxidation states. They have the ability to form complexes. Hey, hello, whole chapter we have done just now, right? And they obviously have presence of empty d orbitals, and these all factors make them good catalytic. They make them good catalysis. Now let's have a look at which are the elements that are used highly in these catalysis, right? Let's talk about iron. Iron is used in Haber's process, everybody. I'm pretty sure that you have read about it. Haber's process, nitrogen plus 3H2, when we do, you get 2NH3. And by the way, this is a reversible process, if you know. And in this case, we also use a promoter. That promoter is molybdenum. And you also have the atmospheric pressure given here. The temperature is given here. You remember all of this. We have studied this in P block also. In the beginning of the session, we have studied this in P block, isn't it? Yes. So in Haber's process, iron is used. Okay, they may ask you catalytic properties, catalysis. Yes, they do ask you, guys. They do ask you. Okay. All right. Now moving on. Ostwald's process. How many of you remember Ostwald's process? In Ostwald's process, you use platinized asbestos. So platinum. See, platinum you're going to use. Yes. Then you have contact process. Contact process, what do you make? Sulfuric acid. Sulfuric acid, here also you use vanadium pentaoxide, V2O5. Okay. V2O5, again, when it is used, you also have to use 673 to 723 Kelvin. So this is also a catalyst. Apart from that, you have Ziegler-Natta catalyst. Yes, Ziegler-Natta catalyst, I think you used to study about it in the polymer chapter when you had to convert ethane to polythene, right? When you had to convert ethene to polythene, that's when we read about Ziegler-Natta catalyst, which is not there anymore, but they may ask you about this. Yes, what is Ziegler-Natta catalyst, everybody? Let me just write it here. Ziegler-Natta catalyst, everyone, is TiCl4 plus Et3Al, isn't it? Et3Al. Yes, this is your Ziegler-Natta catalyst. Okay. Yes, they may ask you, guys. They may ask you. All right. Apart from that, what else is there? Aromatization. Yes, aromatization. You also have in organic chemistry, you have which is it? Which catalyst is used for aromatization, everybody? Forgotten it. Which one was it? Al2O3 plus Cr2O3. Yes. Al2O3 plus Cr2O3. This is used for aromatization. You will read it in your organic chemistry. Okay? You will read it. Chalo. Alright, guys, everybody. Now, You all know that D block elements, they are also known to form interstitial compounds. What is this interstitial compound? I've just told you, remember they have huge surface area, right? They have huge surface area, so that means their atoms are also bigger. Sometimes what happens, the small atoms, right? The small atoms like hydrogen, nitrogen, carbon or boron, they get trapped in those gaps like this. Do you see? Like this blue ones, they get trapped here, okay? They get trapped here, and these, they form interstitial compounds, right? Now when they form interstitial compounds, you have to understand that the stoichiometry is slightly distorted, right? The stoichiometry is distorted, and that is why you get to see FeO 0.98. Array, how come 0.98 oxygen will combine with Fe? That cannot happen, but this is only happening because of this interstitial compounds. They have very high melting point. They're very hard, especially sometimes when boron gets trapped, right? When boron gets trapped, the hardness goes up to the extremities of diamonds sometimes. Yes, it is that hard, everybody. It gets that hard. That is why, see, some borides approach diamond in hardness. And by the way, metals are still there, right? The metallic atoms are still there, so they will obviously maintain their metallic conductivity. Chalo, now, the question is that why do these D block elements, why do they form complex compounds? They form complex compound because they are slightly smaller size of metal ions. Okay, now you might think that, ma'am, what are you talking, ma'am? Right now only you said that these are bigger. Now you're saying smaller. Arey baba, they are smaller than the group 1 and group 2 elements now. Yes, sodium, magnesium, beryllium, they're huge in size, isn't it? But here, obviously, Z effective has increased. So slightly it is smaller. But obviously, they are bigger than the P block elements, right? Yes. That's what I'm telling you. So they have high charge on ions. They increase E by M ratio. Charge by mass ratio is more. And they have obviously availability of vacant d orbitals for bond formation. So that is why they form complexes. Okay? Alloy formation. What is alloy? Nothing. Mix it up all together. All the metals you mix it up. What you get is your alloy. Okay? For example, brass. When do you get brass? Brass you get when you mix Zn plus Sn, right? I don't know. I can't remember. Can somebody tell me? When do you get brass? Or what do you call it? There is steel. Stainless steel. Yes. When you have stainless steel, you have carbon, you have iron, you have chromium, and you have nickel, I guess. Again, okay, now my mind is not working. I think you can check it out later, okay? Yeah. Moving on. Achha, atomic radius. What happens to atomic radius? Now we know that atomic radius. Achha, yes. Here it is very nice. Okay, here it is very nice. Let's understand this a little better. Okay, let's understand this a little better, everybody. Are you all ready, guys? Are you all ready? Yes. Are you all ready? Okay. So first of all, we know that in this case, what happens is left to right when we move, right? Z effective increases. So we know that the metal atoms are supposed to be smaller. But here actually there are two things that are working. Number one is obviously Z effective increases. So what happens? The atoms become smaller. But there is also inside the atom, there is some kind of repulsion that is happening. And when that happens, what happens? The atomic size becomes bigger. So what we see is somewhere from here to here, we see that the atomic size is decreasing. Then we see somewhere here, it remains constant. And then we see that again, right here, this is increasing. Why? Because the repulsion became much. The repulsion became a little more, which is why this happens. Okay, which is why this happens. Then why we are talking about atomic radius? See, this is what I was telling you. Yes. So if there are less number of electrons in the d orbital, the nuclear charge predominates. That means Z effective is more. Now, what happens is as you go this side, now when you go this side, what is happening? The electron repulsion predominates. There are more number of electrons also. The penultimate shell and the ultimate shell, those electrons, they repel each other, hence the size becomes a little bigger. So this is the graph that you see. So you see that it's not constantly just decreasing or it's not constantly just increasing. So there is a trend, and the trend is that from scandium to chromium, you see it increases. Then from manganese to nickel, it almost stays similar. From nickel to zinc, it again increases. Do you see, everybody? Do you see? Okay, Naga, got it. Thank you so much. No problem, no problem. Yes, everybody understood this, guys? Everybody understood this? Yes? Okay. All right, everybody. Now, while we are talking about atomic radius, here is something that is important and something that is very interesting is that, everybody, lanthanoid contraction. What is this lanthanoid contraction? Now, we know that in the lanthanides, the F block elements, right, what happens is there is a constant decrease in the radius. Why so? Because the F orbitals, they are absolutely horrible in shielding, right? They are absolutely horrible in shielding, and the nucleus can very easily see the last electron, and it can hold on to the last electron, which is why what happens is there is a very poor shielding of F orbitals and the size of the atom becomes less. And this lanthanoid contraction has effect on the D block, which is why you see that zirconium and hafnium almost similar size, niobium and tantalum almost similar size, molybdenum and tungsten almost similar size, everybody. Yeah, clear, guys? Okay. Now when we talk about ionization energy, once again we understand that as the Z effective increases, if the Z effective increases, then what happens? If the Z effective increases, but choose, then ionization energy will also increase now. So we just saw that because of lanthanoid contraction, if the radius is getting, atomic radius is getting smaller, that means what is happening? Ionization energy will increase, because we know that atomic radius and ionization energy are inversely proportional, right? It is inversely proportional. So we get to see this. Okay. All right. And similarly, you will see that, okay, here, this graph. Yes, I was finding this graph, everybody. So because of this graph, you get to see, here it has increased. Here it has increased, right? Yes, everybody. And you also get to see, certain things like, what did I say? So you have titanium, then you have zirconium, and then you have hafnium, right? From titanium to zirconium, when you go, you see that the zirconium has lesser ionization energy. But the moment you go from zirconium to hafnium, you see that hafnium has more ionization energy. Why? Why? Why does hafnium has more ionization energy? Lanthanoid contraction, yeah. Just explained to you, right? Lanthanoid contraction. That is why. Okay. All right, everybody. Then we also understand that Cr plus, chromium plus, is greater than, chromium plus has more stability than Mn plus. Why? Why? Because chromium, the moment, okay, have a look. You have 4s1, 3d5 in chromium, right? So if it is plus, that means it gives away one electron, but 3d5 it has, right? It has only 3d5. But for manganese has what? Atomic number 25. That means it has 3d5, 4s2. If it gives away one electron, it will still have 4s1, and it still wants to give away the other electron. Hence, the stability of Cr plus 3 is more than Mn plus. And we know that half-filled orbitals are stable. Cool? Alright, yes, have you understood, guys? Guys, just give me some time. I think we will be done very soon. Acha, so this was the oxidation state which I had already explained it to you, and this is why I told you, see, apart from scandium, everywhere else you see plus 2, plus 2, plus 2, plus 2, plus 2, plus 2. Yes, plus 2, plus 2, right? Do you see that, everyone? That is why we say that this plus 2 is the most common oxidation state. Clear? Acha, one more thing let me explain to you, bacha. Okay, here let's talk a little bit about the oxides, which I did teach you during your P block elements, but once again let me teach you this, everybody. If the elements, if the metals are in plus 2, plus 3, plus 4, what is it going to be? It is going to be basic oxide. Basic oxide, okay? If it is in plus 5, plus 6, plus 7, then it is going to be acidic oxide. And plus 4 oxidation state, usually, generally, plus 4 oxidation state is your neutral or amphoteric, not neutral, amphoteric oxide. Okay, this will be amphoteric oxide. Yes, everybody? Yes, yes, yes. Done? Cool? Understood? This I had taught you, right? This I had taught you. And I also told you that, what was it? Alia and Zoya sang Punjabi song. Alia, Zoya sang Punjabi song, fetched Aishwarya crores. These are the amphoteric oxides, okay? These are the amphoteric oxides, okay? SS meaning, what is SS, bacha? Oh yeah, I am tired, but it's okay. You have exam. You have exam. That calls for much more sacrifice than me just standing here, everybody. It's fine. Acha. Here. Okay, now if you are asked questions like, why is Mn+2 strong? Mn+2 is more stable than Mn+4. How will you explain? Acha, Mn+2, what is the electronic configuration? 3d5, just that, right? If it is Mn+4, that means that it is 3d5, 4 is 2, 2 from 4 is gone, and 2 from 3d5 gone, so it will have 3d3. Now 3d3 is not going to be as stable as half filled 3d5, right? It's not gonna be like that, correct? So that is why you see the stability. So most of the stability questions that you see from D block, you have to understand that they are actually going to ask you regarding the electronic configuration. Yes, Sai Krishna, tell me, bacha, what happened? What is the what no clarity you have? What is it that I haven't taught you? No clarity as in video, or no clarity in what I'm teaching you? Tell me. Yes. Okay guys, everybody, now moving on to magnetic properties. Magnetic properties I have already explained to you in the coordination compound chapter that I have taken just before this, and I told you that paramagnetism is directly proportional to number of unpaired electrons. The more number of unpaired electrons that you have, more is going to be the Bohr magneton. Okay, more is going to be the Bohr magneton. That means more is going to be the paramagnetic. So for example, if Mn is in +2 oxidation state, that means it is going to have 3d5, 5 unpaired electron, guys. Great Bohr magneton, isn't it? Yes, that is why we are saying that paramagnetism is directly proportional to number of unpaired electrons that I have taught you. Chal, questions. Let's do questions, everybody. Let's do questions. After that, we are just left with the, what do you call it? What was it? Potassium permanganate and potassium dichromate. That's it we have to do. That's it we have to do. Just potassium permanganate and potassium dichromate, and then we are done. Okay. That also I will take just little bit of it, and then we will be done. Chalo, chalo, chalo. Everybody, come on. Magnetic moment 2.84 Bohr magneton is given by which atom, guys? Oh my god, this is so simple. This is so easy, everybody. You just have to quickly calculate which one has 2 unpaired electrons. If the magnetic moment is 2.84, that means there are 2 unpaired electrons. Everybody, Ni, nickel has 28 atomic number. So if nickel is in +2 oxidation state, that means nickel will have 3d8. If it is 3d8, draw the structure and find out what will you have. 1, 2, 3, 4 and 5, right? So 1, 2, 3, 4, 5, 6, 7, 8. 2 unpaired electron. That's your answer. That's your answer. Easy peasy? Yes? Easy peasy, everybody? Organic Pahul sir will help you. Yeah, Pahul sir is great at organic. Don't worry, you are in good hands. Now, and guys, this was asked in JEE Mains 2015. This was asked in JEE Mains 2015. Can you believe it? Can you believe it? Such easy question. Next question. Which of the following ions does not liberate hydrogen gas on reaction with dilute acid? Pretty simple, pretty easy, everybody. Correct answer is Mn+2. Mn+2 does not liberate hydrogen gas. You know why? Because Mn+2 is in a stable state, isn't it? Mn+2, the moment it gives away 2 electrons, it is in 3d5, and in 3d5 we all know that it is in a stable state, guys. So that's what. Next, the spin-only magnetic moment in units of Bohr magneton of Ni+2 in aqueous solution would be. We have just calculated it. Ni plus 2. Ni will have what? 2 unpaired electron. 2 unpaired electron bole to option C 2.82. This is going to be the answer. Chalo. Which of the following ions has the maximum magnetic moment? Again, see, very simple, very easy. Mn plus 2 will have 5 unpaired electrons. So, option A is the correct answer. Moving on. Now we come to potassium permanganate, everybody. This is the most important part. From here, guaranteed one question may come in your exam paper. Almost in every shift, I think you will be able to see one question. Okay, so be very careful and listen to it. Do not skip it. Please listen. First of all, we can make, yes, chal. How do we prepare? How do we prepare potassium permanganate? First of all, we have to understand that we prepare it from pyrolusite ore. What do? We take pyrolusite ore. If you have had metallurgy, you would have known what is pyrolusite ore. But now you just know that we will take pyrolusite ore, that is MnO2. This is what we will take. Now this MnO2, manganese dioxide, you know what it does? It gets oxidized slowly. It gets oxidized slowly. So first, MnO2, it is in +4 oxidation state. Now it is going to go to +6 oxidation state, and then it is going to go to +7 oxidation state. So that means from MnO2 it will become MnO4 2-, and from MnO4 2-, it is going to go to MnO4-, which is your permanganate ion. Yes. Alright, so from pyrolusite ore, we are going to take MnO2, everybody. But with MnO2, we will need a base, that is KOH. Okay, we are going to take KOH plus obviously some amount of oxygen. When we do that, now what do we get? I have just told you, you will be getting MnO4 2-, and right here you have Mn in +6 oxidation state. Now after doing this, now what we are going to do is, we're going to put it in an acidic medium. We have just taken a base. After taking the base, now we're going to do acidic solution. Once we take acidic solution, what do we get? Now we will be getting MnO4-, in which it is in +7 oxidation state. Alright, so this was your laboratory method. Now let's go to commercial method, everybody. Now we go to commercial method. So commercially, how can we prepare? Commercially also very simple, very easy. Obviously, you will be taking here also MnO2. Once you take MnO2, now here what you do is simple, fused with KOH, okay? Fused with KOH, alright? Oxidized with air, or you take KNO3. KNO3 is also a very good oxidizing agent, yes? When you do that, what do you get here? You will be getting +6, of course. So MnO4 2-, +6 oxidation state. You get that. Now what you do is, now you are going to do electrolytic oxidation in alkaline solution. Yes, what are you going to do? Electrolytic oxidation. This is commercial preparation, guys. Electrolytic oxidation in alkaline solution. All right. Now what will you be getting? MnO4-, and this right here, it is in +7 oxidation state. Clear hai? Yes. After this, another way to make it is, another way that you can do it is, you can also take MnO4-, okay, MnO4-, and if you just heat it, what will you be getting? You will be getting MnO4 2-, plus you will be getting MnO2, plus you will be getting O2. Alright guys, this is clear? This is clear, everybody? Yes? Yes? Chalo, cool. Now, moving on, everybody. Moving on. Let us have a look at certain, what do I say? Let's call this as trick. Okay, let's call this as trick, everybody. Please have a look. MnO4-, if we put it in a neutral solution, it is going to give you MnO2. In this case, it is in +4 oxidation state, right? Yes. If I put it in a basic solution, then what will I be getting? I will be getting MnO4 2-. If I put it in an acidic medium, then what will I be getting? I will be getting Mn plus 2. Are you getting my point, everybody? Are you getting my point? Yes? Great. Now let us quickly look at the reactions, everyone. Let us quickly look at the reactions, everybody. Chalo. Here are the reactions. Okay. So we have just realized that KMnO4 or permanganate, right? Potassium permanganate in H plus, that is an acidic medium, right? KMnO4 with H plus, that is an acidic medium. Yes, in acidic medium, what is going to happen? What is going to happen? Have a look. Let's say if we take Fe plus 2. If I take here Fe plus 2, this is the easiest example, guys. This is the easiest example, everyone. If I take Fe plus 2 with KMnO4, what am I going to get? What am I going to get? Anybody, any idea, guys? Come on. Quick. Fe plus 2. Fe plus 2 likes to stay in which state? I'm sure you know. I'm very sure you know. I am very sure, absolutely sure that you know, guys. Come on. We have just studied, everybody. Yes, we have just studied, guys. Fe plus 2 likes to go to Fe plus 3, baba. Because what is it? It has 3d6, 4s2. So 4s2 and 1 from 3d6, if it gives away, then it has 3d5. 3d5 is a stable state. So it will get up to, it will go to Fe plus 3, and we just saw here, everybody, see, in acidic medium it gives Mn plus 2, right? So just write here Mn plus 2. Okay. Next, everybody. Next, let's take potassium iodide. So potassium iodide, how can you write it? Potassium iodide, if you take it, it will dissociate, right? It will have K plus I minus. So that means that I minus, from minus it will go to I2, elemental state. In elemental state you have zero oxidation state, isn't it? Plus Mn plus 2. Now can you remember the reactions? Yes. When you look at your NCERT and when you see so many reactions, you get terrified. Yes. Chalo. Now next one, everybody. Let's take H2S. Let's take H2S. When you take H2S, remove the H2, what do you get? S2 minus oxidation state. So from 2 minus, what will it form? It will form S precipitate, zero oxidation state here. Chalo. Now next one, let's take sulfurous acid, that is H2SO3. Very simple, very easy. What will you get here? You will be getting sulfuric acid, that is H2SO4 plus Mn plus 2. Make it sense? Great. Okay. Now let's say that if I take oxalic acid is what? C2O4 2 minus, oxalate to ion, isn't it? Yes, if I do this, that means right here C2O4 2 minus, find out what is carbon's oxidation state. Carbon is in plus 3 oxidation state. From plus 3 oxidation state, it will go to plus 4 oxidation state. Yes, so that means it will go to CO2 plus Mn plus 2. Make it sense? Yes. Yes. And similarly, will you be able to do all the other ones? Yes. Similarly, will you be able to do all the other ones? Will you be able to? Yes. Chalo. Now, if we take everybody, let me just copy this. I'll quickly finish this, everybody. Yes. Potassium permanganate and potassium dichromate. We are almost done. Just give me another 10 minutes. I think 12 o'clock we will be able to finish it. 12 o'clock we will be able to finish it. Pakka. Chalo. Now let's go to neutral. Okay. Let's go to neutral medium. If we go to neutral medium, what are we going to get, everybody? Yes. How do I start class tomorrow? 6 o'clock to 8:30. Somebody will take, no? Okay. Yes. So now we are taking MnO4 minus, right? MnO4 minus. Now let's again take I minus. If we take I minus, this time it will take it to IO3 minus. And in neutral medium, what did we get, guys? See, in neutral medium, we were getting MnO2. So for everything, you have to just write here MnO2. Now have a look at your book. Have a look at your book and find out, are the reactions looking as scary as what you were finding it to be. Yes. Now, if we take thiosulfate ion is S2O3 2 minus. If we take thiosulfate ion, then we will be getting SO4 2 minus plus obviously MnO2. That's it. These are your reactions. These are your reactions, right? Aren't these your reactions? Great. Now everybody, let us go to preparation of potassium dichromate. Okay, what do we have? We have potassium dichromate, guys. Now, potassium dichromate, everyone, what do? We take chromite ore. Okay. 1%. It's still looking scary. Is it? Is it? It's still looking scary. It should not be, bacha. Why are you still finding it scary? See now, exactly what I told you. Exactly what I told you. See? See what is written here? Oxalate ion or oxalic acid is oxidized. See? 5C2O4 2 minus to 10CO2. This is what you're getting. This is what you're getting. I've just told you the easier ions that I have taken, right? Now, potassium dichromate, everybody. For potassium dichromate, what do we take? For potassium dichromate, we are going to take chromite ore, right? So, chromite ore, everyone, is... So, chromite ore, everybody, is FeCr2O4. Yes? So, now, what are we going to do is, chalo, have a look. FeCr2O4. And we add Na2CO3 plus some oxygen. How to remember this? You will remember this as natocro4. How will you remember? Natocro. Yes, natocro. The first thing that you get here is natocro. So, Na2CrO4. This is the first thing that you get. So, Na2CrO4 done. Now, what are the things that are left with you? So, you will have Fe2O3, Fe2O3. This is what you will be getting. Plus, you are left with carbon and oxygen. So, CO2. Make sense? Make sense? Great. Now that you have Na2CrO4, here add some H2SO4. When you add some H2SO4, you are going to get Na2Cr2O7. You are getting sodium dichromate. Now, when you get sodium dichromate, you did not want it, so just add some KCl, and now you will be getting K2Cr2O7, and that is it, okay? And that is it. All right, everybody. Yes, so similarly, let's do the reactions, everyone. Quickly, let's do the reactions, guys. Are you all with me, everybody? Chalo. Yes, here. Let's have a look. For K2Cr2O7, yes. Let's take first of all Fe plus 2. What will we get? We will be getting once again Fe plus 3 plus Cr plus 3. Alright. Now if I take iodine, that is I minus. If I take I minus, then I will be getting I2 plus Cr plus 3. Right? If I take H2S, what will I be getting? I will be getting sulfur like this and Cr plus 3. Right? Similar to potassium permanganate. So these were the reactions. There are certain other reactions which are also there in your book. It's also written here, everybody. Please just go through them. Let's quickly solve some questions and then I'm going to let you go, everyone. Chalo. When a small amount of KMnO4 is added to concentrated H2SO4, a green oily compound is obtained which is highly explosive. Which one is highly explosive, everybody? Out of this, everyone, you have to know that it is Mn2O7 that is highly explosive, and that is the answer. Alright? Chalo. I think enough is enough. Nobody is really interested right now. Let's stop the class. And everybody, let me quickly tell you that in Vedantu's Telegram channel, we will be sending you certain DPPs, and also you have DPPs right below this video in the description box. You can test yourself, everyone. Let me show you right here, everybody. If you just go to our YouTube channel, this is our YouTube channel, and you will see that. So let's say that this is our
ಯಾರು ಅಡ್ಮಿಟ್ ಆಗಿದ್ದಾರಪ್ಪ?
And you can see that this is
you in the description box. You can test yourself, everyone. Let me show you right here, everybody. If you just go to our YouTube channel, this is our YouTube channel, and you will see that
everybody, the moment you click on it, everybody, you will be able to see that you just have to give your email or phone number and you can solve the DPPs. Every single day you will be getting DPPs, my dear students. Every single day, after every session, you will be getting DPPs. So please solve them. It will be really, really helpful for you. Also, let me tell you that right here, right now, we have also launched our last crash course, which is only for 3,000 rupees, everybody. Just for 3,000 rupees, we have launched our Gadar crash course. If you want, you must go and join, because many teachers like Vinay sir, Shilpi ma'am, Harshpriyam sir, they're all teaching there. You must go and just use my code NBJCC coupon code. All right. Yes, with this note, everybody, I think that's it for today's session. I'll see you all in the next session. Tada, bye bye. Thank you so much. You guys are the sweetest. You guys are the best, everyone. Yes, thank you so much. Keep coming. Stay tuned to the session, and I want more Josh for my next session. Okay, guys.